Hello, everyone, to the morning session. I think we are kind of ready to start. Okay. The first speaker of the morning session is Cecilia Gonzalez, an expert on random dynamical system, and she will speak on the title on the board.
All right, thanks very much, Talia. And I would like to thank the organizers of this event. So Irina, Tanya, and Carlo, thanks for the invitation and thanks for bringing us together. And what I want to talk about today is based on various joint works with my collaborator, Gary Froyland from UNSW in Sydney, and also Anthony Quas from Victoria in Canada. And I want to start with a relatively long introduction. It will be, we're going to start hopefully from the very, very beginning, talking about very simple dynamical systems first, then some random dynamical systems. And we're going to be building a little bit of complexity, talking about Ulam scheme and transfer operators. And one of the motivations, big motivations for the work comes from trying to develop ergodic theory tools to analyze transport in complex systems such as geophysical flows. And this is how we're going to be talking about multiplicative ergodic theory as a tool to a spectral type tool to investigate transport in random dynamical systems. So then at the end, I'm going to give you a couple examples where we have been able to really get the most out of these tools and get very precise information out of this. So we start very, very basic. So we, for the moment, think we are in the context of autonomous systems, so classical dynamical systems. We're going to be talking in discrete time. So we have a map T from state space to itself. So that just tells us how the system evolves in one time unit. Of course, if we want to know how the system evolves in n steps, we just have to take powers of this map. And to keep things very, very simple, let's just, for the moment, think that we're even with a linear system and even in R2. So that's represented, the dynamics would be represented by multiplication by a 2x2 matrix. And to keep the transport example in mind, let's just give the example in the context of Markov chains. So the 2x2 matrix will be a stochastic matrix, so entries between 0 and 1, columns adding up to 1. And I believe most of you, if not all of you, are familiar with this type of examples where this is a model of Markov chain model of transport. But let me just say a couple more words about this just to make sure everyone is on the same page. So this could be an example of, say, a country which has, say, two states, the city and the beach. And at the end of each month, each person decides whether to remain where they are or to move to the other location. And if this decision is taken according to some probabilistic process where the probabilities of each of the transitions are dictated by the entries in this matrix, that's how we arrive to this Markov chain model of transport, right? So for instance, here, the probability that if we start at the city of remaining at the city after one step is 90%, of going to the beach is 10%, and so on. Okay, so just a couple words about the state of the system. So if the person starts at the city, we could think of as the initial condition 1, 0. And then after one step, what we get is the first column of this matrix, and it encodes the probability of the person being at each of the two states after one step. And of course, if we want to repeat this for several steps, what we get is just powers of this matrix, and the state would be really encoding the probabilities of being in each of the two states in this case. Okay, but this is the context of autonomous systems. We want to talk about non-autonomous systems. So I think one of the most natural ways to get there is to think that, well, maybe these decisions, they are not always taken using the same rule, but there may be some external factors affecting this. For instance, it may be that the previous matrix tells us what the decisions, how they are made when it's cold, but maybe when it's hot, if we're at the beach, we want to remain at the beach, or if we're in the city, we want to go to the beach with a higher probability. So let's say there's a couple or even more possible evolution rules. And the idea in random dynamical systems is to consider all these evolution rules and think that the way in which this next rule is chosen depends on the completely external system to the one we are observing. So for instance, the weather, right? So there's no connection between what we are observing and what the weather is, and we model this external system as having its own dynamics. So we call the base of the random dynamical system sigma. Okay, so just some conditions. So we assume that the base of this dynamical system, we impose some structure. So we assume this is an ergodic invertible measure preserving dynamical system. And this allows us to model various different environments. So for instance, the autonomous case could be just encoded in a 1-point space omega. The case of seasonal forcing could be encoded, for instance, by taking an irrational rotation, which preserves Lebesgue measure on the circle. And if the weather is completely random, for instance, given by the outcome of a coin flipping experiment, we could take omega to be by infinite sequences of heads and tails, and perhaps P could be a product of Bernoulli measures and sigma the shift. Okay, so there's quite a range of environments that fit in this framework. Okay, so random dynamical systems for us then will consist of these base dynamics. Then there will be a family of evolution rules. For now, we're going to assume they are linear, but of course, we'll have to come back to this shortly if we want, especially to be able to model some nonlinear behavior like the ones which are our motivations, say geophysical flows, or even simpler systems which are nonlinear dynamical systems. We'll come back to this shortly. But for now, random or non-autonomous dynamical system will be this tuple encoding the driving system, the linear space, and the evolution rules. And the way to go forward in time using this random dynamical system is following what is called the co-cycle rule, which consists of composing the different operators according to the trajectory of the environment under sigma. Okay, so L omega compose L sigma omega all the way up to L sigma n minus 1. Okay, and in our examples, where in the autonomous case, we always have the same rule. When we have deterministic forcing, for instance, quasi-periodic, well, we get this quite regular pattern of weather pattern. But if we have some noisy weather, for instance, if we get head, tails, and so on, we get cold, hot, and so on. Okay. So those are the three main examples, and also a few words about notation. The most common term here is random dynamical systems. I also like to use the term non-autonomous dynamical systems, but there are other names: cube products, co-cycles, forced, time-dependent system. There are some subtleties, but in this talk, I'll just be using all those words. They're abbreviated RDS, and there are a couple monographs on the subject, classical monographs by Kiefer and Arnold. Okay, so let's now go back to what happens if we want to model nonlinear systems using a scheme like this. And one really nice idea of how to do this goes back to Ulam. So Ulam, he's the same who invented the Monte Carlo experiments. And his idea to encode nonlinear systems in a linear system is as follows. So for instance, say we want to encode this flow in, say, on the square. So the idea of Ulam is to approximate this with a Markov chain. So the states would be obtained by making a partition of this state space, say on 16 beans. Those would be, the beans would be the states of the Markov chain. And the transition probabilities could be obtained by seeding various initial conditions on each of these beans and counting the proportion of, what proportion of initial conditions starting in bean 1 remain in bean 1 or move to the other beans. So in this case, for instance, since trajectories can only stay in bean 1 or 2, or move to 2, 3, or 4, only these 4 entries in the first column would be non-zero and everything else would be 0. Okay, but this, of course, it's just an approximation. It may be seem quite naive, it's actually quite surprising that it does give some meaningful results in some complicated systems. We'll come back briefly to this later. And of course, one can try to refine this approximation. One can try to get smaller bins or seed more initial conditions. But in this way, we will only get approximations of the dynamics, right? So we will never see the full dynamics in this way. We'll just be approximating. So if we really want to capture all the dynamics in a linear way, that's how we get to transfer operators. So the idea is with transfer operators, instead of looking at the dynamics at the level of particles, we think of the dynamics at the level of densities or mass distributions. Okay, and formally these operators, so we saw them yesterday in Caroline's talk, they are defined as the adjoint of the Koopman operator or composition operator. And I think more useful, at least intuitively, is to think that if one has some mass distribution, so for instance, if we're thinking of ocean flow, we can think that we have some floaters, we drop them at the coast in Pisa, and we see how these floaters distribute, say, after 1 day. So this would be, say, the image of the initial distribution with the transfer operator. Okay, so the price we pay in general is that the space of densities has to be infinite dimensional. Okay, so we have to think of these as integrable functions or perhaps more regular functions, even in the case of one-dimensional dynamics. So that's the price one pays. But if the dynamics are sufficiently nice, for instance, expanding or hyperbolic, it's often possible to find some linear space where this operator is linear and it's bounded and it also has good spectral properties. And these are useful to investigate transport in ergodic properties of the system. So this is, I'm going to give an example in the context this kind of intermediate complexity model. So we're no longer in Markov chains. We're of course not talking about geophysical flows. So we're going to be talking here about one-dimensional maps. So these are examples of the maps that we're going to be composing here. These are class of maps that were initially studied in this context by Lasota, York in the 70s, and later also by Richlik and Keller in the 80s. And assuming these are piecewise smooth and expanding maps, what they were able to show was if one looks at the transfer operator of these maps acting on the space of functions of bounded variation, what one gets is that spectral information gives information about the ergodic properties of the system. For instance, 1 is always the leading eigenvalue of this operator, and it's ergodic and it's simple when the system is ergodic. The eigenvector corresponding to eigenvalue 1 tells us about the absolutely continuous invariant measure of the system, or something like the stationary measure of the Markov chain, if you like. And if the second eigenvalue is strictly less than 1 in magnitude, we have something like a mixing property or some decay of correlations. And one way to visualize this is if we think that we initially have different mass distributions and we apply the transfer operator a few times, what we see is that these distributions are kind of becoming closer and closer together, and they're actually getting the shape of this first eigenvector F1. Okay, so that's how this started. Later in the 90s, a group of applied mathematicians in Germany, Delnitz, Stoffelhardt, Junge, Schutte, and collaborators, they also suggested that if one looks at other eigenvectors and eigenvalues, these can also give some information about the ergodic properties or the transport properties in the system. For instance, if one has a system with two nearly invariant sets or two weakly interacting components, like in this picture, one could expect that the second eigenvector would somehow separate these two components, for instance, giving positive weight to one side and negative weight to the other side. So that's all in the context of autonomous transfer operators, and there are still several questions open there. There's been quite a bit of progress, but again, we want to come back to the context of random or non-autonomous systems. So let me remind you, so we have, in this case, an external system, driving system sigma, a collection of different evolution rules T omega, which could be some of these piecewise expanding maps. And by the way, we saw some examples of this type in yesterday's talk by Charlene. And we will be looking at the transfer operators associated to these maps. So these are the linear operators that we can study with our random dynamical systems tools. Okay. So in this case, the random dynamical system, as before, collects the information of the driving system, the linear space, and the transfer operators, and evolution starting in environment omega and going n steps forward is according to the cocycle rule. Okay, so if we want to have something like spectral, some spectral type decomposition that helps us understand what happens in the case of random systems, that's how we get to multiplicative ergodic theory. So in one sentence, what multiplicative ergodic theory gives us is a spectral type decomposition for random dynamical systems. And this decomposition is of the linear space X into nonlinear time-varying modes. And these are ordered by decay rate. Okay, so just to make the comparison with the autonomous case, so one has to have some good spectral or some good information about the linear operators, quasi-compactness. There's also a version in the random case. And instead of eigenvalues, one has what are called the Lyapunov exponents. And instead of eigenspaces, one has the so-called Oseledets spaces. Okay, and just this picture, I mean, it's just 2 lines, but one can think of this E1, it's the space spanned by the, say, first eigenvector, which is, say, the invariant measure for the system. The second eigenspace could be spanned, say, by this eigenvector, which separates 2 nearly invariant components, and there could be more eigenspaces here. Okay, and in the case of random systems, so the Oseledets spaces are different in the sense that they are not fixed, they are changing over time, or they depend on the environment. But there's, say, a first Oseledets space which gets mapped to the first space, a second space which gets mapped to the second space, and so on. And the next difference is that we don't have information about one-step expansion or contraction, as in the case of eigenvectors, but rather we have information about the long-term exponential rate of growth or decay given by the Lyapunov exponents. So these are the main differences. Let me, before getting into some of the more recent or more interesting examples, I want to go back to the simple case, because I think it's the simplest case where one can see non-trivial examples of how these Oseledets spaces look like. So let's go back to the 2-state Markov chain. So in the autonomous case, where we have just one matrix, so this matrix has leading eigenvalue 1, and this is the leading eigenvector 0.11667, 0.8333. And what that tells us, according to the Perron-Frobenius theorem, is that this gives us the long-term behavior of the system. Okay, and this we can read from this graph. So on the horizontal axis, we have time. On the vertical axis, we have the probability of finding, say, the person in at the city. So if initially the person is at the city, we have this blue dot here. After one step, we have 50% chance of finding the person at the city. And if we wait, say, for 1 year, the probability of finding that person at the city will be given pretty much by this number 0.1667. Okay. Now, if instead the person starts at the beach, well, initially this probability is 0. Then it becomes 0.1 and so on. And again, in less than 1 year, we see that the probability of finding this person at the city is pretty much 0.1667. Okay, so this is as I said, the Perron-Frobenius theorem. In the long term, we have convergence to this equilibrium. Now, what happens when we have some forcing or some randomness? So let's give an example of periodic forcing first. So let's say we have something like 3 hot months and 9 cold months, and these are repeated periodically. So what do we observe? So what we observe in the long term is more complicated behavior, right? I mean, we cannot expect to have something as simple because we have this more complex environment. But and in this case, it's actually a periodic pattern. But what remains similar is that independently of the initial condition, say after less than 1 year, the probability of finding the person at the city or at the beach is independent of where they start. Okay, so these purple modes basically tell us the long-term behavior of independently of the initial condition. And when we have more general forcing, of course, the long-term behavior is perhaps more complicated and it reflects the complexities of the environment. But when multiplicative ergodic theory applies, what we have is this loss of memory of the initial condition. So independently of the initial condition, after say 1 year, what we see is this common behavior or these common probabilities independent of where the persons started initially. And one can think of these purple modes as, say, the first entry of the first Oseledets space in this case. Okay, so it really captures the long-term behavior of the system. So as I said, this is the simplest case. Let me say a few words about history of multiplicative ergodic theory. This goes back to the 60s, starting with work of Oseledets and then Raghunathan in the context of invertible matrices. Then as people became interested in more applied problems, they developed infinite dimensional versions of this theory. For instance, Ruel was interested in hydrodynamic turbulence, and he developed a result in the context of Hilbert spaces. And then other people like Magnet, Thielen, Lian, Blumenthal, they developed different generalizations in the context of Banach spaces. And I should say there are many other multiplicative ergodic theorems. They have been used in other situations, but I have listed here the ones which are closest to the setting we work with. What this first set of results have in common is that they all need to have the matrices or the operators invertible or at least injective to recover these splitting, Oseledets splitting. Okay, and unfortunately for transfer operators, even in the case of these piecewise expanding interval maps, we have that these operators are not invertible. Okay, so that's why Froiland, Lloyd, and Quast, around the year 2010, they developed the so-called semi-invertible multiplicative ergodic theorems, where they do assume that the driving is invertible, but the matrices or the operators may or may not be invertible. And they first developed the result for matrices, and then they extended for some types of operators. And then I also became involved, and we developed even more general results. So at the theoretical level, we are at this point rather satisfied with the state of the theory. But of course, then we are really interested to see examples or how this can be used in some more concrete applications. Okay, so in particular, in the context of transfer operators, so what would give multiplicative ergodic theorems if they apply in the context of transfer operators? So the Lyapunov exponents would be generalizing something that are called the Ruel-Polycott resonances. And there would be at most countably many Lyapunov exponents outside, say, bounded below by some constant kappa star, and the leading Lyapunov exponent will be 0, corresponding to eigenvalue 1 in the autonomous case. And associated to each of these Lyapunov exponent, there would be a finite dimensional Oseledets space. All the vectors in this Oseledets space will grow or decay at the rate given by the Lyapunov exponent. And possibly there will be a complementary space, V, which may be infinite dimensional, but it's closed and every vector there decays faster. Okay, so in this equivariant, unique, measurable splitting, really the most important part in terms of the long-term behavior is encoded in these finite dimensional space, Oseledets spaces. And just to fix some notation, we're going to denote the Lyapunov exponents with multiplicity by mu's. So mu1 will be 0, and then mu2, mu3, so on. And it was known even before this was put in the context of multiplicative ergodic theory, but let me use this language anyways, by Kiefer and Bouzy. So they both investigated this, what we call now the first Oseledets space in this context, and they were able to show that this encodes the long-term behavior or the long-term statistical behavior of the system in a similar way as, say, the stationary distributions for Markov chains. And the second Lyapunov exponent tells us about rate of correlation decay in this system. But now that we have multiplicative ergodic theory, of course, we can ask about higher modes or higher Lyapunov exponents. And in particular, for instance, the second Oseledets space could capture information of slowly mixing regions or coherent structures, or something that we call metastability that we'll come back to briefly in a little bit. Okay, so now, of course, we have, as I said, we want to see this in some examples. So as often is the case, we have a nice theorem, but we would like to see, what does it give in very concrete examples? Can we use it? Is this something that we can extract information from? And the other big question is what happens when we perturb the system, okay? And this, given especially our motivations to try and develop tools to investigate real, say, physical systems, this is really, really important, right? Because we can have model errors or noise, or be using numerical approximations. And so we would like to understand in this case, what happens, say, to the Lyapunov exponents and to the Oseledets spaces when we perturb the system. In the case of autonomous system, there's a well-known result, very famous result by Keller and Liverani, telling us about stability of the spectrum of transfer operators in the autonomous case. In the non-autonomous situation, the previous results on stability are due to Le Drapier and Young in the context of invertible matrix cocycles, Ox, who related stability of Lyapunov exponents with stability of Oseledets spaces. And in the context of interval maps or circle maps, which are small random perturbations of non-random systems, there are some works by Baladi, Konda, Schmidt, and also Bogenschutz. But we have to be really careful because we know that Lyapunov exponents are quite sensitive or can be quite sensitive. And in particular, their results going back to ideas of Magnet and published in works by Bocchi and Viana, saying that Lyapunov exponents can change drastically under arbitrarily small perturbations. So something to keep in mind, but there's also the belief that continuity or stability of these Lyapunov exponents, small changes with small perturbation, is more the rule rather than the exception. And for instance, last year it was announced or posted on the archive this work by Avila, Eskin, and Viana, showing continuity of Lyapunov exponents for IID products of invertible matrices. Okay, so what can we do for stability? So the first thing we were able to address is stability of the top Oseledets space. So this is, of course, a quite important part of the Oseledets space. It captures the long-term behavior. And in the context of one-dimensional piecewise expanding maps, as I showed before, we were able to show stability of this space or of this component under various types of perturbations, including perturbations by noise or by numerical approximations. For instance, here in the top row, we show approximations for different values of omega of the invariant of the first Oseledets space using the Ulam scheme, and in the second row, it's using Fourier schemes. So they are approximating the same object on the same column. So that doesn't, I mean, that looks relatively, I mean, that looks good. So that's just about the top Oseledets space. If we want to talk about stability for other components, so first we did some investigations in the context of matrix cocycles and also in the context of some compact operators on Hilbert spaces. But what we're really interested in is examples in the context of transfer operator cocycles. That's what I'm going to talk about next. And the first example is going to be in the context of random Blaschke products. So this is a class of functions, so they can be, so what's a Blaschke product or a finite Blaschke product? So this is a formula for finite Blaschke product. So it's written in terms of a complex variable z. The AJs here are the zeros of these Blaschke products. They're assumed to be all inside the unit disk. And these functions, they have the property that they leave the circle invariant. Okay, so one can think of these as transformations of the circle. Okay, yes, interval maps or circle maps if one wishes. And in fact, there are some explicit conditions on the coefficients that ensure that these maps, say, are expanding, and so one can use all this theory we talked about. And when they're expanding on the unit circle, that means that there's a band, there's some annulus around the unit circle whose image completely covers itself. And this is really good to get good functional analytic properties of the transfer operator acting on some so-called Hardy-Hilbert space. Okay, and this is a result, or this is an observation that was realized by Bandlow, Just, and Slipanchuk about 10 years ago. And by the way, I think Julia Slipanchuk, she will be coming here tomorrow, maybe. So before then, I mean, these Blaschke products received quite a bit of attention in other contexts, in complex dynamics, potential theory, and there are also some results which are related to what's being done here, especially results by Martin, Schoop, Sullivan, Tichler, Pujals, and collaborators. So what we are going to be talking about here are random compositions of this type of Blaschke products. So we're going to have, again, an ergodic invertible measure preserving driving, telling us how we are going to compose different Blaschke products. Now we're going to have a family of finite Blaschke products where, for instance, the zeros or the coefficients of the AJs depend on omega. We're going to assume that there is a common annulus to all of them. So we have a good functional analytic framework to work with. And we're going to call L omega the Perron-Frobenius or transfer operator associated to the Blaschke product B omega. And in this case, well, the conditions of the multiplicative ergodic theorem hold, and we can actually understand really well what the Lyapunov exponents for this cocycle look like. In particular, this is there is what we call a random fixed point. So this is a function from omega to the disk. This is so random fixed point means that this equivariance relation holds. So x omega gets mapped to x sigma omega under the dynamics. And this is an attracting fixed point in the pullback sense, meaning that if we start with some initial condition z inside a disk of radius r, and we come back, say, from the distant past, and we see where the image of Z goes, that converges to this random fixed point as n goes to infinity. So it's an attracting fixed point, and it captures all the information needed to describe the spectrum. So that if we define this number lambda as the average of the logarithm of the expansion or the derivative at this random fixed point, that, well, that's always a negative number. It could be minus infinity. And in that case, we're going to have a trivial Lyapunov spectrum. So meaning we're going to have an invariant or a first Oseledets space corresponding to this, say, invariant measure, and then no other resonances or no other Lyapunov exponents. But if this number is finite, then we're going to have an infinite Lyapunov spectrum consisting of multiples of lambda. So that's the main observation here. And in fact, one can say more because one can describe here exactly what the first Oseledets space looks like. I mean, there's a concrete formula. And we can also say quite a bit about the other Oseledets spaces. In particular, we can say that they're two-dimensional. So starting from the second one, they're going to be two-dimensionals, and we're going to be able to find, for instance, say that they have poles of order, say, j+1 at this random fixed point and also at 1 on its conjugate. So we can understand quite well what the Oseledets spaces look like here. Okay, so then we can start asking about what happens when we perturb. And this is how we can find first an example of what we call a phase transition. So for this, we're going to consider random compositions of two Blaschke products. So the first one is this map Z goes to Z square. So that's the doubling map. So everyone here already knew some Blaschke products, even if they didn't before, if they didn't think they did. So the doubling map is a Blaschke product. We're going to be composing either this map or this other Blaschke product. This is also an expanding map of degree 2, analytic map of the circle. And if the probability, so we're going to say compose this in an IID way, and the probability of applying the doubling map is going to be P. So the phase transition here is that when P is less than a half, then the Lyapunov spectrum is full. So this number lambda is finite. And when P is at least a half, then we have a trivial Lyapunov spectrum. Okay, and for instance, this is consistent with the fact that the doubling map has super exponential decay of correlations. Okay. Now, well, how can one show something like that? Well, what we have to understand is this quantity, right? That's the lambda, the one that describes the Lyapunov spectrum. And to understand this quantity, well, we need to find where this random fixed point is. So what we do is we get some information of some bounds on where these random fixed points can lie. And so we are able to get, say, when P is less than a half, some lower bounds given by a convergent series. And similarly, in the other case, one can do a similar analysis. Okay, so it really is about understanding this random fixed point. But perhaps more surprising, and in fact, we didn't expect to find something like this, was to find examples where the Lyapunov spectrum can collapse. Okay, so for this family, the one I just described, if after applying this map, we apply some perturbation, say displacement by some normally distributed noise where the variance is small, say something like epsilon, and we look at the transfer operators associated to those perturbations, it turns out that when P is at least a quarter, we get a trivial Lyapunov spectrum. And so that means that in the range of P between a quarter and a half, we start with a random Blaschke product which has a full Lyapunov spectrum, and arbitrarily small perturbations make the Lyapunov spectrum collapse. Okay, so we were surprised to find this because while we knew there were some examples where Lyapunov exponents could, vary discontinuously or jump. The examples that were known really needed one to be careful about the perturbations to really get this collapse. And here, in some sense, it's somewhat natural family, somewhat natural perturbation where one observes this. And well, then that's just an example, but we were able to show how stability or instability is characterized, what it depends on. And the main idea is that we have to look at whether or not this expansion at the random fixed point gets arbitrarily close to zero or not. If it remains bounded away from zero, we're in the stability case, and that's when, if we take small perturbations of these maps or of these transfer operators, we're going to get convergence of the Lyapunov exponents as epsilon goes to zero. But if this, say, random fixed points gets arbitrarily close to the critical point, then we're going to be in the instability case, meaning that there would be some perturbations, even within the class of Blaschke products, that would make the Lyapunov exponent collapse for arbitrarily small values of epsilon. Okay, so this is a stability and instability criterion. And now, well, which one is more common, right? And so we were able then to show that stability is more common in the sense that if the stable random Blaschke product cocycles form an open and then subset of some Blaschke product, world of Blaschke products. Okay, so that's the case for Blaschke product cocycles. And in the last few minutes, what I want to tell you is about another example where we were able to get some information about the Lyapunov spectrum in the context of metastability. So metastable systems, these are systems which have, say, two or more nearly invariant regions, or two or more states of apparent equilibrium. And this is the cartoon picture. So if one starts, say, with some mass distributed somewhere here on the left, and one waits for some time, maybe one gets some, say, nearly uniform distribution on this side before getting seeing that, say, mass can leak to the other side. Okay, and more precisely, one way to define metastability in the context of random dynamical systems, and this is building on ideas of Keller and Liverani in the case of autonomous systems, is to say that the second Lyapunov exponent has to be negative, but very close to zero. And again, we can come back to the case of two-state Markov chains just for an analogy. So metastability could be when these transition probabilities between the different states are small. Okay, and if the transition matrices are given by this, in this simple case, one can explicitly compute the second Lyapunov exponent by this, looking at this integral, and we see that as long as epsilon 1 plus epsilon 2 is non-zero, and if they are small, this would be a negative number and close to zero. So the family in which we investigated this metastability is called pertent maps. This is a family which was introduced by Horan in his thesis. The maps here are parameterized by two numbers, A and B, which tell us about the heights or of these two tents. Okay, this is the formula, but this is the graph. This is more illustrative. And in the case of random pertent maps, we have A and B are functions which depend on omega. And if we want to investigate metastability, well, we scale them by a factor epsilon and let epsilon go to zero. And so that's what we try to investigate. That what Horan showed was that the second Lyapunov exponent was bounded above by a quantity of order epsilon. And in some cases, he was also able to show a lower bound of that same order. And in more few years later, in joint work with Anthony Quast, what we were able to show were order epsilon approximations to this second Lyapunov exponent in this precise family. And the order epsilon term, the coefficient is given by this average of A plus B. And the error is order epsilon squared log 1 on epsilon. And furthermore, we were also able to show that the any third or higher Lyapunov exponent would have to be really far, so around minus log 2 or smaller. So there's a big gap between these two leading Lyapunov exponents and anything else that could be on the spectrum. Last visit to the two-state Markov chain. So one can relate this, or one can try to see how one could get an approximation, a very coarse approximation to the dynamics, but by looking at the Ulam discretization into left interval and right interval. If one looks at the transition probabilities resulting from that discretization, one gets these matrices up to error order epsilon squared. And so, as we said before, one can compute explicitly the Lyapunov exponents for this matrix cocycle, and by Taylor's theorem, we get that the Lyapunov exponents in our theorem and the Lyapunov exponents for this very coarse approximation agree up to error of order epsilon squared log 1 on epsilon. So pretty good approximation. And let me just say a few words about the proof. I will not get very much into it, but one of the ideas, well, we start with some small value of epsilon, and we're going to call holes the parts of the intervals, so that when trajectories get into them, they switch to the other component. Okay, so there some people like to call them windows as opposed to holes. And a key observation is that if one falls in a hole, then one goes to the other side, and it takes a relatively long time for trajectories to come back. Okay, so once a trajectory goes through the hole, it spends a long time in the other component before coming back, like of the order log 1 on epsilon. So this is one important observation, and I will not get very much into this more technical slide, but I will just say that what's important is that we're able to find an invariant set which consists of densities which are nearly constant on each of these two components. And by looking at these invariant sets, we can see how the mass contained in each of the two interval changes under the dynamics. So it changes because mass comes in through the hole and mass goes out through the hole. And one can get some multiplicative estimate on how these integrals or mass changes. By iterating this, we get this multiplicative estimate, and then by Birkhoff-Ergodic theorem, we get some upper bounds on the second Lyapunov exponent, exactly of the form of as in the theorem. And for the lower bound, what we have to do is we can, for instance, look at a very concrete initial condition, say constant +1 on the right, -1 on the left, and see that in that case, the mass also decays at a rate exactly given by, or at least bounded below by this rate as in the theorem. So that allows us to say that the second Lyapunov exponent has this form. And maybe the final thing I want to say is that all these calculations were done kind of omega by omega, so they were not done in a context of multiplicative ergodic theory. And if one wants to put this in a multiplicative ergodic theory context, that's possible. For instance, we can look at this in some kind of fractional Sobolev space. The price we pay is we have to relax the bound on, say, third or higher Lyapunov exponents a little bit, but it's not such a big price. Instead, what we get is we get measurability of these first Oseledets spaces, for instance, when seen as functions to from omega to L1, and also of these multipliers. And for us, it was kind of good and important to be able to put this in a multiplicative ergodic theory framework, also because these results were part of a volume that was published celebrating Professor Oseledets' 80th birthday. So that's what I'm showing in the picture is a photo of Professor Oseledets and myself a few years ago in a conference in China. So that's what I wanted to say. I'll leave you with a summary and happy to take any questions.
Can you say anything about like convergence of the Oseledets splitting itself, or just the exponents? Do the subspaces also converge?
Yes. So there's, I mean, I didn't say much here, but there is a connection between convergence of Lyapunov exponents and convergence of Oseledets spaces. So one should be able to get something like convergence in probability of the Oseledets spaces.
And then one more question. Why is the Oseledets space finite dimensional in this case? Like, why is each one finite dimensional?
Yeah, that comes, I mean, that's part of the abstract theory behind. Let's see, could I, I'm not sure
I don't mean to quiz you, sorry.
reproduce this, but it's part of this abstract
Okay.
theory, and it is related to this quasi-compactness condition.
Other questions?
For the lower bound for the second Lyapunov exponent, is it specific to the context, or it's something you can do in general to get lower bounds?
You mean in the last example?
Exactly, yeah.
So, I mean, this is specific to the context. I think there's some things that can be tried to do. One could try to do more generally. For instance, if one is able to find some good invariant set and good estimates on this invariant set, of course, one could try and get this to work for bounds, but I mean, it can, I mean, it's challenging. I would say it's challenging in general. So it could be a strategy, but I wouldn't want to claim very much generality at this point.
Thank you.
Thank you. Other questions? If not, let's thank. Oh, there is it. Oh.
So on the base space, you always have this invertibility condition. How far does that play a role? How essential is that?
Yeah, that's essential. It's essential to be able to, say, go back in time and push forward from the past. So it really is essential. And yeah, there are counterexamples otherwise.
Okay. Now I guess we can thank Cecilia again. Our next speaker is going to be Mariam Al-Hawaj, and she is going to speak of speak about the generalized pseudo-Anosov map and Hubbard trees. The floor is yours.
Okay, thank you. Thanks for the invitation. And today I'm going to give a talk about generalized pseudo-Anosov from Hubbard trees. So this picture, which is next, sorry, okay. So this picture gives an overview of my talk. And so I'm trying to make an analogy between complex dynamics and geometric topology by having like a Hubbard tree in complex dynamics. I want to construct pseudo-Anosov from geometric topology. So in my talk, I will start with some background from complex dynamics. Then I'll go over the motivation, which comes from geometric topology. And I'll define pseudo-Anosov maps and generalized pseudo-Anosov maps. Then I'll define crossing-free Hubbard trees. And then I'll go over the main results. So I'll start with complex dynamics background. As maybe you all know, that the discrete dynamical systems, we have and a topological space and a continuous map on it. And a very important thing that we work on is an iterative map. This is just a picture of what is an iteration, and then looking at the iteration of a point, the forward iterations of the point x naught in x, then we call this sequence an orbit. Consider now a polynomial on the complex plane. We will define a post-critically finite map to be the map that has the forward orbit of every critical point is finite. So I'll call this map a post-critically finite map. And if we consider the family of all quadratic polynomials on the with parameter c in the complex plane, then I'll define a full-Julia set to be the set of all complex numbers where the forward orbit is going to be bounded. And then I'll take the boundary of this set, and that's going to be called Julia set. And the Mandelbrot set is going to be all parameters c, where the Julia set of Fc is connected. So these now are pictures in the left with the Mandelbrot set. In the right, we have different Julia sets corresponding to different parameter in the Mandelbrot set. So the complement of the Mandelbrot set is a non-empty open set and simply connected. And because of that, then it is simply connected in the Riemann sphere. And because of that, we can use there is the unique Riemann map, the Riemann mapping theorem gives us this unique Riemann map from the complement of the unit disk to the complement of the Mandelbrot set. Now, for an angle theta, we will have an external ray on the outside of the Mandelbrot set. As you can see here, the definition of the external ray, that looking at the images of the external ray from like the outside arc of the, maybe I can point here. So this is the outside of the disk, and I look at the image of that under this phi, that will give me exactly the external ray. Okay, and an external ray, we say that it lands at x if the limit of this is going to go to x as rho goes to 1. So if we go closer and closer to the boundary of the disk, we are going to land on x on the Mandelbrot set. Okay. Now, if we look at, or we consider again a polynomial on the complex plane, a rational angle will determine a post-critically finite map. So starting with a rational angle, we can have a post-critically finite map. And if the map is post-critically finite, then the full Julia set is going to be connected and locally connected, which means that the full Julia set is going to be path connected. And this is important for defining the Hubbard tree. So if f is a quadratic polynomial with critical point, let's say c naught, then if the Julia set is connected and locally connected, then we can define Hubbard tree to be as follows. So it's the forward invariant subset of the full Julia set that contains the critical orbit. So and we can formally look at it as the union of we call them regular arcs, which are we look at the forward orbit of the critical point. In our case, for the quadratic polynomial, it's 0. So we look at the critical orbit and the forward orbit and connecting all those possibilities here. Those are going to be called arcs, and then we will take the union of these regular arcs. So here you can see a full Julia set, and you can see a Hubbard tree inside it. And so this is an example, exactly, where f is a post-critically finite quadratic polynomial. The characteristic angle in this case is theta is equal to 1/5. So you can see this external ray shows the 1/5. And the critical point in this case is periodic of period 4. So this is the critical point. It's going to, so C naught goes to C1, to C2, to C3, and back to C4. Okay? Any question? Okay, so this is the example I have of the Hubbard tree. And here I'm showing exactly what I was talking about in terms of regular arcs. So you can see that the Hubbard tree, which is the union of regular arcs, in this case is C1, C3. So this is one regular arc, and the other one is C2, C3. The union of these two give us the Hubbard tree. And also you can see the external rays that land on the elements of the critical orbit. So you see these are external rays. And you can see also that the angle theta is 1/5. If I divide by 2, this is 1/10, okay? And if I add 1 and divide by 2, I'm getting this. So these are the ones that land on the critical point. Okay. So this is just showing the map, how it's going, the dynamics. And I'll go now to, by this, I'm done with complex dynamics. And I want to go to the next point, which is the motivation to my work, which is coming from geometric topology. So I'm not sure how much you're familiar with geometric topology. But in geometric topology, there are two objects that are attached to a surface. The two objects are a group and a space. Now, what is the group? It's the mapping class group, which is the group of isotopy classes of orientation preserving diffeomorphisms, or sometimes we take homeomorphisms, that restrict the identity on the boundary. And the space is the Teichmüller space, which is a metric space homeomorphic to an open ball, where when what am I saying? When the Euler characteristic, thank you, is negative, this is the space of hyperbolic matrix on the surface up to isotopy. So this is just talking about these objects in the geometric topology. And the main theorem in geometric topology, I'm not sure how much familiar you are, the Nelson-Thurston classification showed that every orientation preserving homeomorphism on a closed surface up to isotopy is one of three. It's either periodic, reducible, or pseudo-Anosov. Now, pseudo-Anosov are have an interesting, objects because they have a huge role in Teichmüller theory. And what I'm doing is trying to connect the complex dynamics with geometric topology by trying to construct pseudo-Anosov from Hubbard trees. So let's see, what is the definition of pseudo-Anosov? It's a homeomorphism on a closed surface such that there is two foliation. So these are the foliation, and it should be a transverse foliation. And there should be a lambda that's greater than 1, such that what does this homeomorphism do exactly is it stretches the one foliation by a factor of lambda and compresses the other foliation by a factor of 1/lambda. So a nice picture of this is this, which shows what is a pseudo-Anosov. So it stretches, but it stays in the same. And there's a story about this picture. I was giving a talk in Atlanta. I was invited by Dan Marglet, and I put this picture, and I didn't say anything about it. And next day, I was, going in a coffee with him, and he was saying, "You know that picture? It's mine." And like I felt, oh my God! So I have this picture, and I have to, give him the credit for this picture. Although some that I heard from others that they don't like the picture. Okay, so maybe I'll produce my own one in the future. So, okay, so going back to the motivation, Fred and Thurston showed that the dilatation, maybe I forgot to mention that we call a lambda a dilatation of the pseudo-Anosov. Okay, so now the theorem by Fred and Thurston, it showed that the dilatation of a pseudo-Anosov is actually a biperon unit, which means that it's a unit which is a real positive algebraic unit whose Galois conjugate lies in the annulus between 1/λ and lambda. And Fred conjectured that, and this is still open, if lambda is a biperon unit, then lambda is the dilatation of some pseudo-Anosov on some surface sigma. All right, so this is the motivation. And the question that I have is, given a quadratic polynomial, can we construct pseudo-Anosov homeomorphism? In another way to say it, if f from T into T, that's the Hubbard tree, is a post-critically finite map, is there an extension of f such that phi is a generalized pseudo-Anosov? So what do I mean by generalized pseudo-Anosov? Here the definition. So it is a homeomorphism, or I'll start with a homeomorphism on a surface S of smooth surface is called a generalized pseudo-Anosov if there are a finite phi invariant set, sigma. So my surface is S, but I have now here another set, sigma. And I have a pair of transverse measured foliations of S minus sigma with countably many pronged singularities, which accumulate on each point of sigma and have no other accumulation points. So think about this as we have the pronged singularities that we might have like countably many of them that accumulate at finitely many points. And there should be also a real number lambda, which is greater than 1, such that it does the same as the pseudo-Anosov. It stretches in one direction, compresses on the other direction. Okay, any question? Can get time? Okay, so going back to the question I started, can we find a continuous map from a pseudo-Anosov to F, to the polynomial? Okay, and my construction or what I'm looking at are finding which Hubbard trees that I can construct pseudo-Anosov from and which that I cannot. And I found that some can and some not. And the criteria is to have that these Hubbard trees have to be crossing-free non-degenerate. So non-degenerate, what I mean by it, it's that the critical point is in the middle between two branches. I'll call upper branch and lower branch, okay? And crossing free, the definition is here. So again, this is denoting BU and BL for upper and lower branches. And the definition of crossing free is as follows. So a Hubbard tree is said to be crossing free if there exists an embedding of T into the plane C that satisfies the following. So the image of the upper branch, or the lower branch in this case, can be isotoped while fixing the endpoints of T into a tree that does not intersect the interior of the image of the upper branch as here. And if T or T, I'll call T is crossing or have a crossing if there is no such an embedding. So again, what do I mean? I look at the tree, the critical point in the middle between an upper and lower branches. And I look at the image of these two branches, the images. And if I can isotope the lower image from the upper image with fixing the vertices, if I can isotope them apart, then I will say that this Hubbard tree is a crossing-free Hubbard tree. Otherwise, it has crossing. And I found in my result that I can construct generalized pseudo-Anosov in the case that it is a crossing-free Hubbard tree. So these are examples of a tree with like a crossing free, and there is a tree with a crossing. So you can see this is the tree, this is the upper and lower branches, this is the image. So this is exactly the same example that I started with. So if should I go back and show you the example? So the example, you can see that this point is going here, here, here. So the upper branch, looking at this part, this is going to be mapped exactly to the whole thing, right? Whereas the lower branch is mapped exactly to this part. So you can see it here. The upper branch is going to everything, whereas the blue is going just here. And you can see that easily I can also isotope them apart, fixing the endpoints. So in this case, this is a crossing free. In this case, there is a crossing because if I fix the endpoints, you can see that this part cannot be isotoped. So I will always have an intersection there. Any question? Okay. So going to the result, okay? So the result says that if T is a crossing-free non-degenerate Hubbard tree, then generalized pseudo-Anosov can be constructed. Otherwise, we cannot. So I start here with a Hubbard tree that's crossing-free and non-degenerate. I can produce a generalized pseudo-Anosov. Okay, so the rest of the talk, I'll go over showing the construction by using an example. Okay, so so this is also a one-to like sorry, if and only if theorem. So in one direction it's by construction, the other direction is an easier that I will just give a brief idea of or sketch of proof about the second part. So let's start with the first direction, and I'll just use my example. So you can see this is the Hubbard tree that I know it's a crossing free and non-degenerate. And so the idea is that I'll take the tree, I'll thicken the tree. So thickening the tree is just like thickening it, as you can see. Okay, so these colored parts are called junctions, and in between there will be sides. Okay, not slides. Okay, sides, and sometimes n stars. So maybe when I have a branch point, I'll call that an n star. Okay, so this is a thick tree, and then I will define a thick map on this thick tree. So this thick map will take the tree into itself, the thick tree into itself. It takes junctions to junctions, and we'll see. So I'll have here the definitions. So a thick tree is a closed topological two-disk consisting of junctions and sides. Junctions represent vertices and post-critical set of the Hubbard tree, respectively. Okay, so actually, yeah, I'm not writing everything. So respectively was for two types of junctions. There's the inner junctions and the end junctions. So I don't want to go over everything, but I have respectively, so I have to explain that. Sides are n stars that represent the thickening of the edges of the Hubbard tree and neighborhoods of an n-valence branch point in the Hubbard tree. So this is an n star. So for example, here we will have a 3 star. Okay. And then we say that the n star connects the junctions if the components of the inner boundary of x is the n star, are contained in the boundary of the junctions. So in this case, I'll say that the n star connects junctions. So usually I'll say, for example, in this 5 star, let's look at where is P1, P2. Okay, so this green one will be connected to a junction. All the greens are connected to junctions, and I'll say this n star connects junctions J1 to J5 if the components of the inner boundary of the n star are contained in the boundary of the junction. Okay, and then we will define a thick tree map, which is a continuous orientation preserving map that takes T into itself. F is homomorphism onto its image. And if J a junction, then the image is inside a junction. The boundary, if we have 2 junctions, okay, where the image of one is inside the other one, then the image of the boundary is going to be inside the other boundary. And if X is an n star connecting junctions, then f of X, the image, is also an n star connecting the images of these junctions. Okay, so, and we will associate to this thick tree map a transition Markov matrix. So we look at number of times the image of one side crosses the other side. So if I think of even the n star, which is in this case 3 star, I can think of it as 3 sides attached, okay? And then I will look at the image of each of these. So for example, maybe I'll draw this. So in the example that I have, okay, so maybe I can think of this as 3 sides, okay? And then I will look at each side where it crosses. And then in this case, in this example, I'll have a 4x4 matrix. So for example, the side one, so if I look at, maybe it's easier to look at the tree itself, okay, which is the same, to represent these sides. So, so let's say this is S1, S1, S2, S3, and S4, okay? So we look at S1, the image of it, which actually this whole thing is going here. So the image of S1 crosses the second one. So that's why we have the one on the second one here. And so on. So we look at, for example, S3. This S3 is mapped to the whole thing. So you can see the third, we have ones in the first and on the last one. So this is the transition matrix. And then we define a tree-like train track to be a family of vertices and curves embedded on a surface such that the following hold. Too many things. So the idea, I'm not sure if you've heard of train tracks before. Did you? Do you know? No? Okay, so maybe I should talk about. So think about train track, really, like, you know, in a train. So for example, something like this, it goes and comes back. So it could be a, you know, a train track, but in my case, it's a tree-like train track because sometimes I have branch points. So for example, in my picture here, this is the inside part is a train track, a tree-like train track, because also we have, so there are switches where places that you can go and come back. Yeah, so, and let's go maybe quickly on the definition. So there are finitely many vertices of 2 types. There are switches and branch points. There are countably many curves. So usually train tracks have maximum of 3. In my case, they have countably many curves of 2 types, edges and loops. And away from vertices, the curves are smooth and do not intersect. The endpoints of each curve are vertices. And if the endpoints of curves are the same point, then we call it a loop, if it goes and comes back to itself. Otherwise, it's called an edge, okay? And at branch points, only edges, sorry, checking my time. Yeah, so, okay, where am I? At branch points, only edges can meet, and at switches, edges are loops, and loops can meet. And at each switch, there are countably many curves, and the union of all edges is actually a topological tree. So anyway, so I'll see how I'm building this train track, tree-like train track. So I'll start with the middle of these sides, okay? And in this case, I'll have a disconnected train track. And then, so that is tau naught. And then I'll do maybe going over the pictures is faster. So I'll start with the map. I'll start with this tau naught, and I hope you can see it. I'll apply the map here. So what happens to the upper? It's going to the whole thing. The lower is going to be here. And then what I'll do some isotopies, which just think about it as compressing everything to the middle. And then I'll apply the map again. You can see what's happening because of the critical point. There is a loop forming, right? And then I'll do the isotopies, compress everything, I'm having a loop. And then again, so this loop is moving to the red goes here, and there's another loop forming. Again, compressing. Continuing this way, you can see that there will be infinite loops forming in all these sides. So going, maybe this is like a zoom, zooming to the left part in the top, if you couldn't see small pictures. So again, what I'm doing is this. Any question on how is this going? Okay, I hope. Okay, and from there, I'll start by using the Markov matrix. Again, I can find the Markov matrix using my train track. So the train track I found was something like this. Here, loops, 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 and loops, so infinitely many. And then, so you will look at these sides as your, to form this Markov matrix. So these are like a 4x4 matrix representing these. And finding the eigenvalue of this and eigenvector, the left and right of them. And then, so these are the two eigenvectors where, 4 tuples in this case. And I'll take each, like x and y, each coordinates, x1 cross y1, to be the dimensions of a rectangle. So I'll be forming 4 rectangles. The dimensions are coming from these eigenvectors. And then, so these are the 4 rectangles I'm forming. And then I will glue these rectangles. So by gluing, you can see I have this, and applying the map to each part of these rectangles, you can see what's happening. There's a squishing and, decomposing of this, which gives me, but this is not all. I have to also identify the sides. So these parts represent the loops. So I'll just do the identification according to the loops from the train track. And in between, the yellow and orange parts are coming from looking at how the map was, for example, I know that this is mapped to the whole thing. So I know also that this is critical point, and I know this part goes here. So I figured out how to identify the sides. And at the end, I'm getting the pseudo-Anosov. So in summary, the theorem says that if T is a crossing-free non-degenerate Hubbard tree, then we can construct pseudo-Anosov. Otherwise, we cannot. The other direction, I can maybe, if anyone is interested, I can say it later. You can come to me and ask me. And I did this. So I looked at my kitchen. I found this rice bag. So I did actually measure with the same as my example, and I found that actually this is a hyperbolic angle forming. I still need to identify all the sides, and actually it will close into a sphere. And that's all. Thank you.
So at the end of your construction, I don't really understand where does the pseudo-Anosov property with the 2 foliation come from? How do you show at the end that this map is pseudo-Anosov?
How did I show this?
Yes.
Yeah. Okay.
Where do you see the foliations and the
okay.
dilatation?
Okay. Okay. So lambda that I found is actually the dilatation.
Okay.
And so this is okay. So we can think of, this is a good question. We can think of these, maybe looking at the picture. So I have, so you can actually think of these are going to be the foliation.
So you have
because this is now a singularity, and then there is the transverse foliation, right? I'm doing it right. Yeah, and actually this is what I'm using for the other direction of the proof.
So I would like to know maybe just the idea of the other direction too.
Do you want me to do it now or?
Or maybe after.
Okay, okay. Sure.
Another quick question. If not, let's sing Mariam again. To the morning session, and we are happy to have Sakshi Jain speaking of piecewise contracting system.
Yeah, thank you so much, all the organizers and all the participants also to be here. Today I am talking about, okay, I see that I have a typo in the title. Yeah, I can blame it on jet lag, but I'm not jet lagged and I didn't prepare this afterwards. Anyway, so I'll be talking on piecewise contracting systems, and this is based on joint work with my PhD advisor, Carlangelo Liverani. So why do we want to talk about piecewise contracting systems at all? So the idea is that we are interested in these systems with discontinuities, and precisely hyperbolic systems with discontinuities. But the problem is that when we study dynamic hyperbolic systems with discontinuities, there haven't been a lot of results when you talk about higher dimensions, or when you talk about nasty discontinuities, for example, I don't know, non-Markov discontinuities. And so the idea was to divide the problem somehow. We don't know how efficient is that idea, but okay, to divide the problem somehow into two cases. So we talk about piecewise expanding cases and piecewise contracting cases as separate cases, and try to see if it can help us somehow to deduce things about discontinuous hyperbolic systems. So this would be the piece about piecewise contracting systems. So there has been some work in this area. To be honest, there has been a lot of work in one dimension, so like interval maps, when they are piecewise contracting systems on interval maps, and in higher dimensions also. But overall, under some nice assumptions that they had to assume, perhaps for the sake of proofs, I guess. But what they have proved more or less is that generically, the behavior is that the attractor consists of periodic orbits for any given piecewise contracting system, generically. And that is actually also what we have proved, but I would say that we have loosened the hypothesis on our systems a little bit as compared to what the things are there in the literature already. And okay. So the system would be as follows. We have a compact subspace. Let's say it is an RD, but it is applicable also to general metric spaces. Okay, the domain is a compact subspace, and T is a function which I will call as piecewise contraction if it satisfies certain conditions. So first of all, I would like to partition my domain into open subsets, such that the closures, okay, such that the closures combine together to give me the domain, and that the function is restricted to each partition element is a uniform contraction. So there exists some lambda in 0, 1 such that it satisfies this particular condition here. Okay, and maybe through the course of this presentation, we would add some assumptions on our system, on our function, or on our space for the sake of results. Okay, and the attractor, this is the usual definition of attractor, nothing new, but okay, it would be defined as the intersection of the images of the space, the closures of the images of the space. And I would say that the partition that I had defined in the last slide would be called a maximal partition if it satisfies that the union of the boundaries of all partition element is actually the set of discontinuities of space. So it is, I'm not refining the partition any further, let's say. Okay, now example on the board. So I also didn't get time to make an example for the presentation, let's say. And I also like to construct it on the board along with the audience, let's say. Okay, so what I'm trying to show here is that, okay, as I said in my introduction, in the history slide, that generically speaking, the attractor of a piecewise contraction actually consists of periodic orbits, but in some certain cases there can be an attractor which is actually a Cantor set, and we would be looking at such an example here. Okay. Okay. It would be a three-dimensional example, and let's first of all consider this unit triangle. And I divide it into two halves, T1 and T2, let's say. And this is the point, half and half. And I hope everybody can read what I'm writing. If not, you can ask me. All right. And then I define a map which maps these triangles as follows. So again, the same triangle. I may not have to write this. Okay, let's say there is some alpha which is in 0 and 1/2, and I'm mapping this so that both of the triangles T1 and T2 map inside this smaller triangle here. All right. And then to get into third dimension, let's define these maps. Phi1 Z is lambda 1 Z, and phi 2 Z is Z minus 1, where these lambda 1 and lambda 2, again, because we are talking about contractions, always in 0, 1. Okay, and then I would define a map from X, which is this, if this triangle was T, then it is T cross 0, 1. So this is the domain. And the domain looks a little bit like the following. Okay, and all right. And you see this partition here gives me a partition here, which kind of looks like this. Sorry. And let's say this is X1 and this is X2. All right, and the image would look something like following. So f of X1 would be something like this. This is f of X1. Okay, and this is actually like a prism, let's say, a smaller prism inside this. And similarly, f of X2 would be like this. Goodness, it is so difficult. I don't know, maybe I'm not able to draw this anymore. Okay, a copy of something like this also at the bottom. And so this is f of X2. All right. On the same triangle. Yes, yes, yes. Yes, and okay, and now we can see that half of these, this f of X1 is inside X1, and half of this is inside X2. And if I take further iterates, it would divide like this. It will, okay, maybe another color. Okay, so it would divide like this, half here and half. Yeah, okay, yes. Half would be here somewhere. And similarly, if I take iterate on f of x2, it would also divide into 2 halves. And if we keep taking these iterates, I will get a Cantor set which is actually lying on this line, which is 0 cross 0, 1. And there would be a Cantor set lying on this, which is actually the attractor of this map here. All right. Maybe I didn't write the function, and I should. Okay. At the end, the function, what is it? And is really alpha of x minus y, 2y, and phi 1 of z, if x, y are in T1, and alpha 2x y minus x, phi 2z otherwise. Okay. Well, there is a reason that I construct an example like this. Well, it is not really my construction, but okay. I give an example like this to show you that a piecewise contracted system can have an attractor which is actually a Cantor set and not a periodic orbit. You can also construct them in one dimension as well, but I just want to motivate that in higher dimensions there are things going on which may not be so visible in one dimensions, let's say. And yeah, okay, for that matter, we study them in higher dimensions. Okay, now getting back to study how generically I'm claiming that I would be seeing that the attractor consists of periodic orbits. All right. So I define this notion called stabilization of partition when I would say a partition of a piecewise contraction stabilizes if for any two partition elements it satisfies that there exists some natural number for which that iterate of a partition element lies completely inside other partition element. And let's remember here that these partition elements are open sets. So when I'm saying that this is lying inside this partition element Q, I mean to say I would like to emphasize that it is entirely inside Q and has nothing to do with the boundary of Q here. All right. And least such n here would be called as stabilization time of my partition. Yes. And let's call the, did I already give the, I don't remember. Okay, maybe I talked about maximal partition, but I would revise it that the maximal partition is the one which has the boundary set as the discontinuity set of the function. So it's not a refinement of the discontinuity partition of continuity. All right, and I would call my piecewise contraction as Markov map if it satisfies that the maximal partition stabilizes for that particular function. Well, in general, maybe you are familiar with Markov maps for expanding systems and not so much with contracting systems, but it is really the same thing because I'm saying if you think about the definition that you consider in case of expanding systems, that the okay, I don't see a duster. Okay, I do. Okay, so in case of piecewise expanding systems, we say that a partition is Markov if it satisfies that there exists for an iteration such that Fn of P, if P is a partition element, is intersects with any other partition element, implies that it is contained in, sorry, it implies that Q is contained entirely inside this thing, or it is disjoint from that partition element. It is the same thing if you think of it as in case of piecewise contractions and you take negative iterates of the function. Okay, so I will call it as Markov map, and then I have my first result, which is that if there's an equivalence in between these two conditions, that the attractor is disjoint from the set of discontinuities and that the function that I'm considering is Markov, and also it satisfies that if my function is Markov, then the attractor consists of periodic orbits. Okay, and then I would like to say how this characteristic is in fact generic. So for genericity, I should be saying what is my topology or what is the metric that I'm talking about on my class of functions here. So if I have any two piecewise contractions with maximal partitions, so and so, then I define this set as the set of homeomorphism, as the collection of homeomorphisms which satisfies that the partition element of one are mapped onto the partition elements of others under a homeomorphism. And then the metric is given as this particular thing here, where I say that if that set is this is this is empty. So if the set is empty, then it is some constant. So just for the sake of finiteness of the metric, and if it is non-empty, so there exists homeomorphisms from the set of partition elements of one to the other, then the metric is defined as follows. Okay, and then there is a distance between the further iterates of the maps. And under this metric, I claim that the set of Markov piecewise contractions is open in the collection of all piecewise contractions under this metric, and also that any two Markov piecewise contractions stabilize at the same time, which are close enough in this metric. Let's remember that the time of stabilization is that n for which the partition element maps inside another one. Okay, and this doesn't really have to do anything with genericity, but because it works with the same metric. So I'm saying that there is some sort of stability, maybe not the regular one, but I'm talking about I will be talking about topological stability, which is a little bit different from regular definition, because here my functions are defined from non-wandering sets of respective maps. And and under these under this definition of topological stability, I'm claiming that the set of Markov piecewise injective contractions. So I didn't say what are piecewise injective contractions, but they are just injective in every partition element. They are topologically stable within the same metric that I defined before. Okay, and then to talk about the density bit, because I'm claiming that this behavior is generic, I showed openness, and now I would like to talk about density. For that, we have to consider actually piecewise smooth contraction. So we have to talk about some smoothness on our function in every piece, just because it doesn't work otherwise. Okay, and so I'm saying that my function is C3 in every piece, in every partition element, and its inverse is C1 in every partition element, and that the boundaries of every partition element are actually C2 d-1 dimensional manifolds, and that there is some transversality in the intersections of two boundaries. Yes, these manifolds are pairwise transversal, and the intersections. Okay, these are just some assumptions that I had to make for the sake of proofs, some smoothness assumptions on the boundary and the map. Okay, and for density, actually, I define, I prove my density with this metric, which is a rather stronger topology. I don't know if a stronger topology is actually a mathematical term, but okay. If the partition elements of two maps are exactly the same, then the distance is defined like this, and it is infinity otherwise. So it is actually a extended metric. And if you remember, the first metric that I talked about was allowing the partition elements to be different. They just had to be homeomorphic image of one another. But here I say that they are at infinite distance if the partition elements are different, and otherwise there is this distance. And then under this metric, the piecewise smooth Markov contractions are D2 dense in this space of piecewise smooth contractions. I would just like to say that this metric seem very restrictive, but it's a good metric if I am able to prove density, because you see when you have a very fine topology, then it's good to have a density result in that topology. Okay, I always get confused in between fine and coarse topology, but I guess this is finer topology than the other one, and that the other one is a coarser topology, and it's good to have a openness result in a coarser topology, let's say. And this metric somehow makes the result stronger and also helps us improving the things with the smoothness conditions, because otherwise we could not really deal with the boundaries, the way that the boundaries maps and etc. And I guess this is it. Yeah, thank you.
Okay, I have a quick question.
Yeah.
So since you can control so well the distance, does it make sense to apply the results of Kerala-Liverani to get the distance between the spectra of the operators?
The thing is that we would like to talk about spectrum of the operator and things like that, but because generically it has periodic attractors, the invariant measures would be just Dirac delta orbits or convex combinations of those. So
Okay.
we don't really think about operators on these because it's not interesting, let's say.
But can you do the same thing for expanding maps, for instance?
Yeah, I mean, yeah, if we use these metrics, sure, but
Yeah.
but I'm not sure if it would be that good, or I don't know, relatively any better than the results that they are already in the literature. Yeah.
Thanks. Other questions? Okay, then let's you.
The first theorem.
Yeah.
Can you go back to the first theorem that you showed us? Just okay, can you quickly say what the role of this set of discontinuities is in this theorem? I didn't quite.
Yeah, so because when I define Markov maps, I say that this image of a partition element after some iterates goes inside another partition element, and these partition elements are open. So I'm forcing that the images kind of move away from the set of discontinuities.
Okay.
So in that sense, when I'm talking about a tractor and I'm taking like further and further iterates, I'm always moving away from the set of discontinuity, and that's why I get this equivalence relation here. See, because a tractor is disjoint from the set of discontinuities.
Okay, thank you. I just wanted to see the condition on the boundary. Can you show it again?
Yeah. Yeah, so the boundaries are C2D minus one-dimensional manifolds, and yeah, and they are pairwise transversal, and the intersection is a manifold also, C2 manifold.
So you want the boundary to be transverse?
Yes.
To each other?
Yeah, so
Okay.
the intersections are transversal, so
okay.
I just don't want to have cusps in the intersection, let's say.
Okay, how can we understand maybe in your proof?
Yeah, I mean, it is a bit involved, but what I prove using this is that the growth of number of partition elements is dominated by the growth of contraction coefficient, let's say. So what I'm trying to say is that when I take further and further iterates of my function, then the things keep dividing. They may keep dividing, but the boundary should allow me that they are dividing at a rate which is lesser than the growth of contraction coefficient, and that somehow this thing plays a role there. It's a little bit involved. I can tell you things in person maybe.
Okay, thank you.
Okay, hello, my name is Colette. I'm going to talk about bifurcation resultants and discriminants for rational maps today, and mostly the work in my thesis, which I just finished about a week ago. Okay, so for this talk, I'm just going to go over the basic definitions that we're going to use for periodic points. So here, the general setting is going to be some rational map on P1 of K, where we're defining some rational map to be some quotient of polynomials f over g, and the degree is d, which is equal to the maximum of the degree of f and g, and we're setting the degree to be greater than or equal to 2 here, and f and g have no common factors by definition. So we say that a point P in P1 of K is n-periodic if it satisfies this identity that phi to the n of P is equal to P for some n greater than or equal to 1. And we say that the orbit of P is also n-periodic since any point Q in this orbit also satisfies this relation, phi to the n of Q is equal to Q. And we say that P is a primitive period n for phi if phi to the n of P is equal to P, so it's n-periodic. And it's not m-periodic for any integer m that's strictly less than n. Okay, and then P is going to be an n-periodic. If P is an n-periodic point for phi, then we define the nth multiplier of phi to be this guy down here. So here, basically, if P is just any n-periodic point, then we specifically define the nth multiplier like for that period n. So a certain point, right, can have many different multipliers depending upon which period for that point that you're talking about for the work that we're doing here. Okay, so I want to introduce the idea of bifurcation using this very basic example from the Mandelbrot set. And then the point of my talk is going to be how we can generalize the idea of bifurcation by describing it algebraically. So let's go over some basics, which I'm sure everybody here in the audience is probably familiar with. So if you consider the polynomial family over the parameters c, z squared plus c, where c is over the complex numbers, then this family defines the Mandelbrot set. Specifically, the Mandelbrot set is this set of all complex numbers c such the orbit of 0 under fc is bounded. Okay, so we're interested here in the hyperbolic components of the Mandelbrot set. So again, definition for hyperbolic components of the Mandelbrot set would be the following. So the hyperbolic components are basically the open connected domains of the Mandelbrot set, where these maps FC have a unique attracting end cycle. So another way of describing that attracting end cycle is that it's an orbit of primitive period n that satisfies this relation on its multiplier. The absolute value of the multiplier has to be strictly less than 1. Okay, so here's basically this famous picture of all the hyperbolic n components. So you have the one component, which is the main cardioid here. You have exactly 1 two-bulb, the 2 components directly to its left. You've got 2, 3 components there and there. And then it's a fact that if you're talking about an n component that's attached to the main cardioid, then you have quotient of n as the number of those components attached to the main cardioid, right? So like there's 2, 3 bulbs attached to the main cardioid because quotient of 3 is equal to 2, right? And there's only 1 two-bulb attached to the main cardioid because quotient of 2 is equal to 1. Okay. So here we're going to talk about the bifurcation points in relation to this picture over here. So the multiplier of that unique attracting cycle that was mentioned, right? Basically like every map C, right? You're thinking of these complex numbers C as maps, right? So every complex number C in one of the hyperbolic n components, right? It's going to have this unique attracting end cycle. So the multiplier of that unique attracting end cycles defines a diffeomorphism between each n component and the unit disk, which extends to a homeomorphism between their closures. And then each of the n components has something called a root. So the root of a particular n component is the boundary point, which gets sent to 1 under this bijection. So just as some quick examples, the root of the main cardioid over here would be this cusp point. And the root of the two-bulb over here would be the bifurcation point C equals -3/4, right? The complex number right here, C equals -3/4. And in general, I'm just gonna move this chair out of my way. In general, the roots of the components, right? So like for each one of the components that you're looking at, if it's an n component, it's going to be attached to some m component where m is some divisor of n that's strictly less than n. So like 2 is attached to the one component over here where like 1, you know, is a divisor of 2. And each component is attached to, right? So each n component is attached to an m component where m is that divisor, like, and there's only one of those points happening, right? There's only like one divisor of m for each n component that you're looking at that it's attached to. So basically that's like how you find a root, how you find the root. So you kind of like here for the main cardioid, this guy is going to be the root. And then for the 2 bulb, this guy right here is going to be the root. And then if you're looking at this 4 bulb over here, the root of this 4 bulb would be this point right here where you've got the 2 and the 4 bulb touching each other. Okay, so anyways, the roots of all of these n components, those are going to be what we call the bifurcation points for, say, the Mandelbrot set. So the bifurcation points of the Mandelbrot set, they're basically all the roots of the hyperbolic components. And they come in 2 types. So type 1 of bifurcation point is some point where an m component meets an n component for some divisor m of n with m strictly less than n. So the multiplier homeomorphism is differentiable at this type of bifurcation point. And a dramatic shift in dynamical behavior also occurs here, namely as the parameter c is varied, the map FC transitions from having an attracting m cycle to an attracting n cycle. So an example of a bifurcation point of type 1 here, would be C equals -3/4, where the main cardioid is meeting the 2 bulb. Okay, so it's basically like bifurcation points of type 1 here. They're the places where an m component is going to touch an n component like that. And then bifurcation point, a bifurcation point of type 2 would be the cusp points of the cardioid shaped components. Okay, and then differentiability of this multiplier homeomorphism fails at these points. All right, so I'm mostly interested in the bifurcation points of type 1. And I'll talk a little bit more about bifurcation points of type 2 here. So let's dive into this example a little bit further. So all maps C and the complex numbers in the one component have an attracting fixed point, right? If you're just looking at like all the points C, right? All the maps C in the main cardioid. And all maps in the 2 component directly to its left have an attracting 2 cycle. And the main cardioid and the 2 bulb meet at this bifurcation point. Like I mentioned, C equals -3/4. And as I mentioned earlier, right, inside of the main cardioid, all of the maps there are going to have this unique attracting 1 cycle, whereas in the 2 bulb over there, all the maps there are going to have this unique attracting 2 cycle. And then if you're looking exactly at the bifurcation point C equals -3/4 at that map, then you kind of have something happening that's in between the 2 things, right? Basically, you're going to have some point P equals -1/2, where you have a neutral, basically that's going to be a neutral fixed point here, meaning that the multiplier has absolute value equal to 1, right? As opposed to like being strictly less than 1. Okay, so how could you generalize the notion of bifurcation? You could talk about the multi-Brot set instead. So if you consider the multi-Brot set, which is basically started by this dynamical system, FC z to the k plus c, where here the exponent k is going to be greater than 2, then the multiplier map is an analytic k-1 fold cover from an n component to the unit disk, which extends to a k-1 fold cover of their closures. And it's known that the closures of distinct n components are distinct, so that the roots of the components, there's going to be a k-1 of them for each n component, are distinct. Okay, and basically, once again, all these roots are what you would call the bifurcation points in that case. And then if you want to keep generalizing, then you kind of just have to pass to this algebraic description because maybe, the geometry is not so simple to see anymore. So for dynamical systems defined by more general polynomial or rational map families, then we're going to get into what this algebraic description is. So in 1995, Morton and Vivaldi described bifurcation points for any monic polynomial with coefficients in an integral domain as the zeros of the discriminants of things called dynatomic polynomials, which we're going to define in the next slide. And in my thesis, I generalized their description of type 1 bifurcation points to the description the case of rational maps of degree D greater than or equal to 2 defined over any field K of characteristic 0. Okay, so let's talk about what these things dynatomic polynomials are. So first we have to introduce some basic definitions. So here, let's go back to our rational map phi, and then we're going to homogenize the rational map phi, right? So basically capital F and G are the capital F and G, right, are the homogenizations of these guys. And then you would define the iterates as so set capital F1 to be equal to capital F, G1 to be equal to G, and then you can define the iterates like this. So then the nth iterate of the rational map phi, you can write as this guy right here. So all these things are maps on P1 of K. Okay, and then we define something called the n period polynomial. So for a rational map, the definition would look like this. And the point of this n period polynomials is that its zeros are going to be exactly all the n periodic points for the rational map phi. Okay, and then we define the nth dynatomic polynomial dn via this recursive relation. So you set Pn, the n period polynomial, to be equal to the product of all these dk, where k range over the divisors of n. So this type of definition might look kind of familiar. Something similar happens with the cyclotomic polynomials, right? Cyclotomic polynomials also have an analogous recursive definition. And in fact, that was the inspiration that Joseph Silverman used when he was defining the dynatomic polynomials. And the idea in this definition was that we wanted to do something analogous to what happens with cyclotomic polynomials. The zeros of cyclotomic polynomials are exactly the primitive nth roots of unity. So the hope here was that the zeros of the dynatomic polynomials would be the points of primitive period n, rather than just, like the n periodic points. But we wanted to narrow in on an algebraic description of the points of primitive period n for the dynamical system. Okay, that didn't turn out to be exactly the case, and we'll go through why in a second, but that was the idea, right? Basically, the hope was that the zeros of the dynatomic polynomials would be exactly the points of primitive period n. Okay, and then also another way you can write the dynatomic polynomials is explicitly as so, using Mobius inversion. So you can also write dn as this product, again, ranging over the divisors k of n. Where here you've got all the pk's raised to mu of n divided by k, where mu is this Mobius function right here. And it is indeed a fact that all the dynatomic polynomials are indeed polynomials. This is a proof that's in Silverman's book on arithmetic dynamics. Okay, so let's say that I'm considering the case of just the polynomial as being my rational map. So say dehomogenize and then write the polynomial as just f of z. So for example, the first dynatomic polynomial, according to that recursive definition or the explicit definition, it's just going to be equal to the one period polynomial, which would be just f of z minus z. And then the second dynatomic polynomial would be p2 over d1. So that looks like this ratio over here. Okay, so let's look at a specific example of a polynomial family. So say you consider the polynomial z squared minus 3/4 on P1 of C. So the third dynatomic polynomial, D3, is this degree 6 polynomial in Z. And the zeros of D3 form a directed graph that consists of 2 3-periodic orbits consisting of distinct 3 periodic points. So the nice part about this example in the case of D3 is that the zeros of D3 correspond to exactly the points of primitive period 3, right? Because when you look at the two orbits formed by the zeros of D3, right? The two orbits are exactly of length 3. Basically, you don't get any repeated points in the orbits. So all the points, right, in the two orbits, they're of primitive period 3. Okay, however, the zeros of Dn in general do not coincide, as I said earlier, with the points of primitive period n for f. So again, let's consider this example of this map z squared minus 3/4 on P1 of C. So if you write out the definition of D1 for this map, it's this polynomial up here at the top, z minus 3/2 times z plus 1/2. And if you write out D2, the second dynatomic polynomial, it simplifies as z plus 1/2 squared. So basically the point P equals negative 1/2. This is a 0 of D2, but it's a primitive period 1, not 2. So basically this idea of having the zeros of the dynatomic polynomials be exactly, you know, like the points of primitive period, and it doesn't happen, as this example shows here. Basically, you have a point, negative 1/2, that's a 0 of D2, but it's of primitive period 1. It's a fixed point. Okay, so then when you draw the orbit of this particular point, basically you've just got 2 copies of the same point in the orbit of length 2. And the reason for why this happens, right, for our case in the dynatomic polynomials as opposed to the cyclotomic polynomial case, is that these n-period polynomials are k-period polynomials. In the definition of the dynatomic polynomials, these guys can have a multiple root, which doesn't get eliminated in the inclusion-exclusion by mu. But however, for cases where those k-period polynomials are separable for all the divisors k of n, the zeros of Dn are indeed going to coincide with the points of primitive period n. Okay, so more generally, the zeros of Dn will correspond to some subset of the n-periodic points, which will also contain all the points of primitive period n, so they're somewhere in between the two. And we call them the points of formal period n for the map phi. Okay, so once again, the points of formal period n, they're just exactly the zeros of the dynatomic polynomials. And then you have this inclusion relation here. So right in the middle, you have the points of formal period n, which again contain the points of primitive period n, and they're all n-periodic, right? They're contained in this set of n-periodic points. Okay, and then a more precise description of what the points of formal period n are can be described by this theorem from Silverman here. So if you have some map phi being a rational map of degree d, if P is a point of formal period n for phi and a point of primitive period m for phi, then one of these 3 situations happen. Either the primitive period m is just equal to m, right? So basically, you know, as I said earlier, all the points of formal period n, they're going to contain the points of primitive period n as well. Or in case 2 over here, the second situation that can happen here, the m could be something less than n. And then that's going to correspond to the multiplier being a primitive R root of unity, where basically R is going to be n divided by m. Okay, and then the third case is just, you know, basically like the same thing, but for characteristic P. Okay, so then let's look further at the question of when a certain rational map has a point of formal period n, whose primitive period m is strictly less than n. So another way of describing this is that it happens when the homogeneous resultant between the 2 dynatomic polynomials is equal to 0. So in other words, there's some point P, which is a common 0 between the 2 dynatomic polynomials for a divisor, so for some divisor m of n that's strictly less than n. Okay, so in Morton Mavaldi's paper, they showed that in this case, the resultant of dm and dn was going to be plus or minus this, this power of these things called delta polynomials. So delta mn is the resultant of the n divided by n cyclotomic polynomial and something else called the multiplier polynomial lambda m, where here lambda m is defined as these multiplier polynomials. So basically the roots of the multiplier polynomials are all of the multipliers of the nu m divided by m orbits. Okay, so nu m is basically the degree in x and y of the mth dynatomic polynomial, And then if you divide by m, which would be the length of all the orbits, then you get like basically the number of orbits that are formed from the roots of the mth dynatomic polynomial. So basically you look at all of the orbits that are formed from the zeros of dm, and then you have the multiplier for each one of the orbits, and then you can form this thing called the multiplier polynomial. Okay, so what is this basically saying? It's saying, you know, if the left-hand side vanishes, which we're thinking, right, the left-hand side, when this resultant vanishes, we're thinking of that as having a point of formal period n, which is a point of primitive period m less than n. That's going to correspond to basically having some point of formal period m whose multiplier is a primitive n divided by nth root of unity. Okay, so let's look at this example again for the polynomial family z squared plus c. So here is basically a table showing a few of these delta polynomials here for various cases of m and n. And then let's go back to this example that we've been looking at here. So if we look at the case of m equal to 1 and then n equal to 2, we see that delta 1, 2 would be the polynomial 3 plus 4c. Okay, so remember we had that bifurcation point c equals -3/4, and we said earlier that there's this point -1/2, which is a fixed point of formal period 2. And now basically we know that the minus the resultant of d1 and d2, that's going to be the same thing as delta 1, 2, as Morton and Vivaldi's theorem would indicate, and then this is going to be equal to 3 plus 4c, so that vanishes at the bifurcation point -3/4. And accordingly, the multiplier for that point P is going to be -1, which is the primitive second root of unity. So it demonstrates everything said in the theorem here with this correspondence. And one of the things that I did in my thesis was prove a similar result for the case of rational maps. So this was my theorem. So if phi, which is again defined as this rational map of degree d greater than or equal to 2, where f and g have no common factors, then if m is a divisor of n that's strictly less than n, then you have that the resultant of dm and dn is going to be equal to plus or minus the resultant of f and g to some power times the delta polynomials defined in the same way for the rational map. So I started working on this problem back in the fall of last year. And then in January, a paper was published where somebody basically proved the exact same thing that I was trying to prove. And their work showed exactly what this exponent formula was going to be. So in my work, I kind of ended up with this complicated exponent formula, nu plus a rho plus sigma tau, and you don't want to know what it is, but it's something complicated. But you can basically show that it simplifies to this formula over here, where by degree in A and B, we mean the homogeneous degree and these coefficients that you see in the definition of the rational map appear of the resultant of these two dynatomic polynomials over 2D, where 2D is the degree in A and B of just the resultant of f and g. And the quick reason for that is that delta mn to the m here, that has to be a regular function on rat D, which is the space of like a moduli space of rational maps of degree D. So then if you write that delta, you know, that power of delta as the quotient resultant dm, dn over plus or minus resultant of f and g to some power, because that thing has to be a regular function, then like the degree of the top in A and B has to be equal to the degree of the bottom in A and B. So then basically this gives you the formula for what that exponent has to be there. Okay, so what is this saying? It's basically saying that the correspondence that Morton and Vivaldi had for their case of just monopolynomials, you know, with coefficients over some integral domain, that correspondence still works for the case of rational maps here, because the resultant of f and g is always going to be non-zero when we define the rational map with no common factors. Okay, So that's what I wrote up here at the top, right? So once again, since the resultant is non-vanishing, then we get the same correspondence that Morton and Vivaldi got. So more explicitly, again, the map phi will have some point of formal period n with primitive period m less than n. That's when the left-hand side, when that resultant formula vanishes, exactly when there's some multiplier lambda n of some point of formal period n, which is a primitive n divided by nth root of unity. And that's when the right-hand side of this identity vanishes. And then furthermore, Morton and Vivaldi's resultant formula was key in proving the main result of their 1995 paper, which was this theorem A, which was a discriminant formula for the dynamic polynomials. So the discriminant formula gives like the full description of all the bifurcation points, the bifurcations of points of type 1 and type 2. So the formula was this down here. So over here in all of these factors, the zeros of these guys are going to be those bifurcation points of type 1 that we talked about. And then whenever delta n vanishes at some map, basically, right, at some map in the moduli space, then that's going to correspond to that map being one of the cusp points of the cardioid shaped, in the case of the Mandelbrot set, like a cusp point of the cardioid shaped components. Okay, and then explicitly delta nn is defined via this relation on the bottom down here. So remember the multiplier polynomial, it's zeros. We're just going to be like all the multipliers. So if you write delta n of 1, then the zeros of this guy are going to basically be the maps where some multiplier is just going to be equal to 1, right? Because here, this guy is going to have to vanish at the same place as this guy. Okay, so that's basically what this is here. So Morton-Vivaldi's discriminant formula implies that for dynamical systems determined by Banach polynomials phi over in an integral domain, right, there's this correspondence between dn having now a multiple root, right, because it is a discriminant formula, right? So if the discriminant vanishes, you've got this multiple root, and then that's going to correspond to this information about the multiplier. So the multiplier is either equal to 1, that's when the delta n's are going to vanish, or you have some multiplier, which is a primitive n divided by nth root of unity for, again, m dividing n and m strictly less than n. Okay, and, you know, again, just going back to the example that we've been looking at here, case 2, right, once again, that just corresponds to C being the boundary point in the Mandelbrot set where you have m periodic and then n periodic hyperbolic components meeting, and then case 1 corresponds to cusp points. Okay, and the eventual goal of my project is to prove the full discriminant formula analogous to the discriminant formula in theorem A over here from Morton and Vivaldi. So that's what I'm like kind of halfway done doing. I got done with the resultant formula, and then I had to type that up and graduate. So next I'm trying to finish the full discriminant formula. Okay, so that's all.
What tools do you use in your proof, and how does that differ from what Okayama used to prove the same thing?
So Okayama used complex potential theory, I think it was called. His proof was completely different than mine, and I actually barely looked at his paper other than just using it to check some results. For me, I just found ways of generalizing what Morton and Vivaldi had done in their approach, just from like a very algebraic perspective. And yeah,
Thanks.
there's a lot of sage involved as well to get some hunch of how things would work out.
There are questions? If not, let's thank the speaker again. Happy to have J.Roda talking about classifying hyperbolic new stationary measures for K3 with large automorphisms.
Thank you so much for allowing me to speak today. So yes, it's a very wordy title. Thanks so much for coming anyway, especially before lunch. So we're going to break down this title. So first of all, we're going to, oh, it's a little bit not as bright. Okay, well, hopefully you can still see. But first of all, we're going to talk about mu stationary measures, what they are, and why we would hope to classify them, because that's the goal here, classifying stationary measures. We're going to ask ourselves why we're allowed to put this hyperbolic condition on them and what that is. We're going to talk about what a K3 is, of course, and then we're going to talk about what it means for it to have a large automorphism group. Okay. So we're doing complex dynamics today. And so whenever I say that, people think these things, right? And I love these things, but that's not what I do at all. So, actually, I'm in the two-dimensional complex setting. X is some compact complex surface, okay? So K3, which we'll see an example of soon, or a complex torus, okay, etc. And let's let X be the set of holomorphic diffeomorphisms here. So these are the maps that we're applying to X. Okay, we will focus in on K3 shortly, but I want to get a little bit into the setting today. Thankfully, Cecilia did a lot of that today. So thank you, Cecilia, wherever you are. I want to make a point that I'm actually in the random dynamical setting, okay? So when most people think about dynamics, they take a single map F, and they iterate it on X, and they ask questions about that. But instead, we're going to take a probability measure, mu, on the automorphisms of X, okay? Oh, weird, okay. All right. So for example, sorry, it's weird, it's like I have to double click. Okay, for example, I can take two automorphisms, and half the time it's F1 and half the time it's F2, okay? So this is a probability measure on the automorphisms. So instead of taking a single map, I draw with respect to mu. Oh, how do I get the pointer? Aha. So the pointer, so with our example here, if I take X, half the time I'm applying F1, and half the time I'm applying F2. So this is what we're thinking of, okay? So maybe we formalize this a little bit, okay? So we take these bi-infinite vectors with the holomorphisms in our support. And we take the left shift, and that just moves everything to the left, the usual shift map. So F1 goes to F0, and F0 goes to F-1, and so on and so forth. Okay? And our dynamics is actually something called the skew product map. So what happens is this picture here, if you like picture. So you take X, you apply the 0th coordinate of the given omega. So omega has some automorphisms in it, right? You take the one at the 0th position, you apply it to X, and then you shift everything over. So here, F1 will be mapped to F0. So the next time I apply capital F, my skew product map, I'm going to hit it with F1, and then F2, and so far, and so on and so forth. And then backwards is kind of similar, notationally painful. And so that's this picture here. So X goes to F0 of X, and here omega gets shifted over. Okay. Any questions about that? Okay. So here's an example. So let's stick with a complex torus for a second, because we like those. So we can kind of describe some of the automorphisms in there. So like GL2Z acts on C in the usual way. Okay, it's by matrix multiplication, and it descends to X. And so we can say it lives in this automorphism group. Okay. So let's give two examples of matrices. This is my favorite matrix of all time, right? You know, the cat map. I'm sure anyone else feels that way. Some other matrix. And we can take our probability measure on the automorphisms as half the time I choose A and half the time I choose B. Okay, so we could take an example of an omega, and here A is at the 0th position, B is at the 1st position. Obviously, you can't list all the elements. And say take 1, 1 here. Then the skew product map applied to X omega, it applies A to the vector X, and then it also shifts everything over. Okay, so now B gets shifted to this. Okay, and now A isn't the pass, it's in the -1 position. Okay, so that is our random dynamical setting. Now, what is a mu stationary measure? Well, a mu stationary measure is one that's invariant on average. We're all very used to invariant measures, but this is this statement here. Okay, so yeah, with our example, mu would have to satisfy a relationship like this. Okay, So now, of course, invariant measures are stationary. That's pretty obvious. If you're invariant, then you're invariant on average. But stationary measures, sorry, invariant measures don't always exist, but stationary measures will always exist in this setting. So that's what they are. Okay, that's something to think about. But let's ask ourselves why we care about them. Okay, so there's something called Bramann's law of large numbers, and this is how we can get a stationary measure. So if I fix an x, for almost every choice of maps that I apply to x, if I take the empirical measure here along the orbit, it turns out that you get something that's mu stationary. Cool, right? Okay, so very similar. But so the reason why we would bother to classify them is the following. So these stationary measures are supported on the closure of the orbit. So a common goal in dynamics is to classify orbit closure, something I'd love to do someday in this setting. And it's actually a really good first step towards this, but there's more work to do, but this is why one might want to do something like this. Okay. Okay. So another quick, kind of silly example, honestly. So if we look back at our matrices again, they have a shared fixed point 0, 0, right? So obviously Dirac on this point is invariant and hence also stationary. But Bramann will also tell us that for almost every choice of vector omega that we take here, we're also going to get a stationary measure. Okay. All right, so now what is hyperbolicity? And why are we allowed to stick this in front of stationary measures? So it's very similar to what you think. So it's hyperbolic if there are no zero Lyapunov exponents. So our exponents are like this. And so Oseledets theorem, which we saw in Cecilia's talk, we have some splitting. We have a stable and unstable Oseledet direction here. And so you'd see the dependence on omega. And it's the usual business of the exponential growth rate. But now instead of, if you see this usually with a single map, now it's, oh, it's actually, I think it's backwards, sorry. You have f omega to the n, you apply f0 first and so on and so forth. Okay, so it's this composition instead. And you, of course, so similar to the single iterate case, you have these global stable and unstable manifolds that we're going to talk about soon when I actually state the result. It's the usual thing. But mine are by almost everywhere by holomorphic to C. So you should be thinking of, complex planes instead. Okay. Okay. Why am I allowed to, or why do I feel that I'm allowed to stick hyperbolic in front of my theorem? Well, it's because they're thought that in this setting, don't jump yet, we haven't finished the setting. All the stationary measures are going to be hyperbolic. So, okay, so if I can save my theorem for the hyperbolic ones, then I'm doing pretty well. So what is this non-elementary thing? Okay, that takes me to the large automorphism group part. We're almost at the K3 part. So we talk about something called a non-elementary actions, the hope that we have to classify stationary measures. And this means that it's going to have a large automorphism group. So the definition exactly is that when I look at the group generated by the supportive gamma, of course, it acts on the second cohomology by pullback. And if this contains a non-abelian free group, then we say it's non-elementary. Okay. And so in particular, it's big because, oh, whoops. I pressed a button. Oh, no, that button. Okay, this button. So the non-abelian free group, like Z star Z, big, right? Big. Okay, and I'm going to show you an example of one of these in a second. It turns out K3s can carry such actions. They're not the only things that can, but we're going to focus in on this for now. Let's talk about what a K3 is, because you're all burning to know. So an example of a K3 surface, and this is just a family. It's not all K3 surfaces, but these K3 surfaces, as we'll show, carry non-elementary actions. So it's called the Waller class, and these are smooth surfaces in P1 cross P1 cross P1 by degree 2, 2, 2. And so this is a little bit of a funny thing if you've never seen this degree 2, 2, 2. But we can think in affine charts as it being this kind of formula here. Okay? And you would compactify it into P1 cross P1 cross P1. In the fine chart, it looks like this. And so let's describe the automorphisms of this K3. Well, if I project X along, and you copy, laser button, onto one of the other two. So say I fix the first copy and the third copy, and I project X onto these two. So it's I equals 2. I have some pi. It turns out to be a 2-to-1 cover. And so there's an involution that exchanges the sheets, and this is an automorphism of X. Okay. Let's be concrete about that for a second. So again, take pi 2. So I fix the first and third copy of P1. And it's actually like fixing X1 and X3 here in this polynomial. So now we have a polynomial where X1 and X3 are fixed. And so in order to land on X, you have to have the zeros of this polynomial with respect to this variable. So this is a polynomial in degree 2. So points on X are zeros here. And so our involution actually just exchanges these roots. So that's an automorphism. Funny enough, it turns out that all these involutions generate the entire automorphism group, and it's a free product. So it's very big. In particular, contains this non-abelian free group and descends to the cohomology. It's still big. So it's big, right? It's very, very big. Okay. So this is my main result. And I don't like having this many words on the slide. It's very wordy. And let's hope that all my blurring actually works on the screen, because I'd like to claim that we know a lot of this. Oh, it is also work in progress, but anyway. So we know what a K3 is, right? Well, at least we have an example in mind of a K3, and that carries a non-elementary action. We know what it means to have a finitely supported probability measure on the automorphisms of X. We understand what it means to be non-elementary, and what it means to be a hyperbolic stationary measure. Okay, so this is on X, and this is, on aught X. Okay, so now there is this little caveat here, which is we need to have no gamma invariant algebraic curve. So we think copy of P1, elliptic curve, higher genus thing, right? Something like this inside. And this we have to have because, or maybe, okay, because we need to have that the Oseledets directions are random in our setting. And this is a theorem of Quentin-Dujardin, who you'll see in a minute. So we have to have this here. Thankfully, actually, our Waller example here, our friend here, is such a family that does not preserve any algebraic curves. So this is not an empty statement at all. Then we actually get something called stiffness. So when stationary measures are invariant, we say that we call this condition stiffness. So they're actually literally invariant. And then there's also this next statement that says the stable and the unstable conditionals are homogeneous. So we're going to give the definition of homogeneous more concretely in a future slide. But if we think about what these conditional measures are, so as I showed you before, we have these globally defined, or these global unstable and stable manifolds. And it turns out that you can construct canonically in a somewhat painful and notationally painful way. So I didn't do it here. This is a short talk. A measure on each. So a leafwise measure, so a measure on each global stable or unstable, and we call these the conditional measures, okay? And yes, so we will get to homogeneous, but further we can actually classify nu. Sorry, I'm gonna call it mu and nu, okay? Is it's either finally supported, it's volume, or it's this kind of funny condition here, which we're gonna spend the remainder of the time talking about, okay? As I think, so we're going to define what it means for them to be jointly integrable, but you can kind of think, but you might already have a notion of what that means, but we're going to get to it, okay? All right. So before we get to that, I'd like to say that Quentin-Dujardin, whose papers I read a lot, in 2023, they proved a very similar result, and it has some further analysis. But the thing is it's not a complete picture of the story because they have to assume existence of parabolic elements. So, but we don't necessarily always need them because non-elementary actions, as it turns out, are generated by hyperbolic elements. So it's when you descend the cohomology, the spectral radius is 1, positive topological entropy. And So it's true that the Walder family actually does have parabolic elements. They are things of this form. These automorphisms, sigma I and sigma j, where I is unequal to j. Okay, they do have these sorts of things, but you know, if you kind of think about this, right? Turns out that there are K3s that carry non-elementary actions that have no parabolics. So this theorem is meant to encapsulate these types. Okay. All right. So further, I'd like to say about something or two about Benoit and Kant. So Benoit and Kant, I used their techniques to prove this theorem in case 2. So we're going to hear from them again. But this theorem in 2011, they did a very similar classification, but in the homogeneous setting. So you have an almost simple Lie group that acts on a homogeneous space. They classify stationary measures as being volume or finitely supported. Okay. So kind of similar classification theorem. And Shaw had proven it 20 years prior, but only in the existence of parabolic elements because he was able to use Ratner. So this is the related work. And I'd like to say one last thing, which is that this paper of Brown, Eskin, Philippe, Rodriguez, Hertz, that you also hear about in Rose's talk is kind of unfinished paper to us, which is in preparation. It's like 250 pages long. I don't know, it's long to me. And we use this to get the invariance of nu. So we basically, there's a proposition there, and we apply it about 3 times in our theorem and use an entropy argument. We will get in the invariance, and I won't really talk so much about that. I'm going to assume it and move on, but I'd like to say that this is where we get it from. Okay, so we're going to focus in on case 2, and we're going to assume that nu is invariant. And I'd also like to say that in the same paper, Brown, Eskin, Philippe, Rodriguez, Hertz, they tell us that the supports in case 2, these conditional, the supports of the conditional measures that we're talking about, are actually one-dimensional real curves. So as we kind of said, the picture, you know, you have some WU or S or whatever, right? It's a copy of C. And you should think that the support curve, which we're going to give a name in a second, is U plus of X omega, is some real curve sitting inside this thing. Okay. And it's unique, very, very important, because that's basically how we get this theorem. Okay. So last part of the theorem that we need to talk about so that we understand every word in it is homogeneity. So you probably already have a notion of what homogeneity is. But anyway, I'm just going to do it in this way. So you have to take for granted for me, please, that there is a thing called normal form coordinates, which is a chart on either the stable or the unstable. Okay. And it conjugates F to a linear action. So in C, this is just, you know, this conformal constant here. And what it means to be homogeneous then is that the support viewed inside C, which is a straight line through the origin, the measure on this is Lebesgue. Okay, so this is my definition of homogeneous. Okay. Now we're gonna define our stable, and you might really hate me for this. Oh, okay, might really hate me for this because you know, our unstables were WU of X omega. And we're going to call the conditional support here as U plus X omega and the stable one. You know, and as much as this is kind of a standard convention, I hate that you use U here and plus here, but U to the U doesn't work out so nicely, and we often call it U. So this is how we're going to denote the conditional supports. And we're going to focus in on case 2, like I said, and I'm finally going to tell you what this jointly integrable thing is, okay? It is the following proposition here and the following picture. So for almost every point X here that I have with some given omega, there, if I draw the stable support curve here, because it's U minus, it can do the same picture for U plus, obviously. I get some neighborhood where almost every point in there, so like Y and Z here, if I draw the unstable, they're going to intersect, okay? So both of these intersect. This is my definition of jointly integrable. Okay. Well, okay. And so yes, again, so I want to focus in on the fact that these each have a unique curve. So how do we prove this theorem? Well, the proofs, well, okay, so first of all, we reduce it to the following. We reduce it to showing that, you know, the stable, which is some, you know, copy of C you should think about, and, you know, and an unstable supports intersect, okay? Oh, I used Y. Are going to intersect instead of the stable support. So it's kind of a different problem, but it turns out that all the permutations of this idea, putting U here, putting minus here, all this stuff, are very similar. And you can use these to build back the proposition. And the technique for doing this actually has a name. It's called the Flooding-Benoit-Kant argument. Obviously, due to Benoit-Kant, this paper with the homogeneous setting classification of stationary measures, and Eskin and Mirzakhani, who put the floating part in 2013, and then Brown, Rodriguez, Hertz, I always want to say the other paper, also used this technique, okay? We work by contradiction, so we assume that the proposition is not true, and we work to demonstrate a contradiction to Brown, Eskin, Philippe, Rodriguez, Hertz, which is the idea that all of these planes only have one support curve. We're going to get two of them in there, and it's going to be a contradiction. Okay. So we only have a few minutes left. Maybe I just kind of like, do I want to draw the picture, or do I want to let you go to lunch? I draw the picture. So the idea, this is a big picture, and we can explain all of it. And there are many choices of parameters here, but I'm just going to say something brief, is that these points here represent support curves. So we're going to fix a support curve here, and we're going to follow them along as we flow by T, and then we flow by M, we flow by L. And in this picture, forward in time, so flowing forwards with the skew product map is going up, and also, unfortunately, to the left, and going down is backwards. We start here at these points. So at these orange points, we pick some omega, which we take the support curves of, and we flow by some T to the next points. We pick another omega. We take those same support curves for this omega, and we're going to follow them along to the green points, pick another omega, follow them along to the black points. And so it's a little unclear why we're doing all this chasing and what are these points up here. They're important, but it's not entirely clear why. But this is kind of the chase that we're going to do. We're going to follow some support curves around. And I'm just going to tell you the end game. So the strategy is I fix some epsilon greater than 0. And for each of these, so for each pair of orange points that we have here, you know, we get some sort of value of L. And that's kind of this last leg of the V, which we flow with respect to this future choice. And we want to end up at 4 so that the support curves are at least epsilon apart. The support curves that we're chasing, this whole funny diagram here, are always epsilon apart for each L. And then when we take L to infinity, which actually amounts, as it turns out, by choice of parameter, to taking the orange points closer and closer and closer together, the stable distance shrinks, and they will end up in the same unstable manifold. And you have two support curves in one manifold, and that is a contradiction to Brown, Eskin, Philippe, Rodriguez, Hertz. Okay? I will stop there, I think. Thank you so much.
I have a question about your main theorem.
Okay.
So
I take back this. Oh, so many animations. I'm so sorry. Okay.
So yeah.
Yeah.
So for case 2, I think you mentioned Benoit-Kant's paper.
Yes.
And the case 2 is something new, right? In this setting.
Yeah.
But
oh, sorry, go ahead.
yeah, and then why the second case appears in K3 case?
Yeah, so it turns out that so Benoit-Kant's case, yes, only has finally supported volume. So it's true that we have examples where this kind of thing, it appears, like, for example, if you have the Waller family and you take the volume restricted to the real points, it will end up in a kind of case like this. This theorem actually also holds for abelian surfaces, which Benoit and Kant cover, and many of the other kinds of compact complex surfaces that carry non-elementary actions, not rational ones necessarily. But yeah, so you would only end up with those two in this case, but there are cases where you end up with 2. And yeah, does that answer your question?
Yeah, and also I wonder, is the number 2 is related to the Lyapunov exponent?
So, I mean, so what kind of, I guess where 2 comes in is kind of falling from Brown, Eskin, Philippe, Rodriguez, Hertz, which is this kind of like, there's some sort of sub-resonance, there's some sort of like algebraic subgroup acting on the unstable of, on the unstables here. And then the 3 cases come in as whether the orbits of that is 0-dimensional, 1-dimensional, or 2-dimensional. Is that kind of it? Is it okay?
Yeah. And also I wondered if it is related to orbit closure, because you mentioned
Yeah.
conjecture.
Yeah, I haven't done this kind of thing yet, so I don't exactly know how to do it yet. But it is, so you can use these kinds of results to say something about orbit closures. Is something that I hope to do soon.
Okay. And also non-elementary condition is related to Zariski-Dens, something like.
Yeah, so the Benoit-Kant paper, so like the whole Zariski-Dens condition, I think is stronger, but it's in the torus case, which they state, which is not their main theorem. It's like the 1.3 or something like that. Then it's not equivalent to non-elementary.
Okay, thank you.
Thank you.
Hello. So, Alexandra, can you hear us?
Yes, I can. Can you hear me?
Yeah, we hear you now. Okay, so welcome. Thank you for joining online. So here, I guess we're ready to start the afternoon session. Are you ready to go as well? The slides work, I guess. Well, it's on your own computer. So. Okay, so then... yeah, we can start. Yeah, so then let's start the afternoon session. So the first speaker is Alexandra Skripchenko, who is giving a talk on interval translation mappings, mysterious relatives of interval exchange transformations. So please go ahead.
Thank you very much for the invitation. I'm very happy to be in Pisa, at least virtually, and I regret a lot that I was not able to join you physically, such a wonderful conference in a very cool company. And today I'm going to tell you about some work in progress, so don't expect incredibly impressive theorems, but I will tell you how we are having fun right now with 2 of my friends and collaborators, Mauro Artigiani and Pascal Hubert. And I will tell you something about ITMs, interval translation mappings. So I would like to start with the definition of the second protagonist of my talk, the interval exchange transformations. So the interval exchange transformation is a very simple combinatorial object. We just take an interval of a real axis. You take your favorite one, for instance, from 0 to 1. Maybe you want it to be a half interval to be 100% sure that you control all the possible subtleties. And then you divide it into parts. Each part is also a subinterval, so you take a partition, and then you mix these parts. So if you want to be more formal, then you have a map from the interval to itself, and this map is piecewise continuous, and on each interval of continuity, it's just a translation. These maps were defined in the 60s. It's very hard always to investigate their history because several great mathematicians arrived to the same idea at the same time. And there are several ways how you can imagine the birth of interval exchange transformations. One thing is that you can see it as a generalization of the rotation of the circle, probably the most powerful dynamical system ever. If you restrict yourself to the case of 2 intervals of continuity, so you ignore the blue guy on my picture and you imagine that you just extend the green one, then you will have nothing else than the rotation on the circle. Another way how they appeared was due to the relations with the rational billiards in polygons. If you consider a polygon whose angles are rational numbers multiplied by pi, and you consider a billiard flow there, so you have a very small ball and it moves, there is a linear flow, and once it touches the boundary, then you have to respect the law of geometric optic and reflect your ball according to this law. So if you play such a billiard, then you will get the interval exchange transformation as the first return map for the smartly chosen transversal. This was another source how they appeared indeed. And the third way why people started to think about them was more related to topology, because 60s was a moment when Thurston was studying his, was building his theory of diffeomorphism of surfaces and so on, and measured foliations on surfaces. And if you consider an oriented foliation on the oriented surface, and this foliation is the measured one, then again, as the first return map to the smartly chosen transversal, you will necessarily get an interval exchange transformation. I probably have to mention some names. So the first approach, which is a generalization of the rotation on the circle, is related to Vladimir Arnold. He was the first person who made the pictures that I present here, when you have an interval exchange transformations on 3 intervals. Later it was generalized on n intervals by Valery Oseledets, who at the time was a student of Yakov Sinai. And at the same time, people who were thinking about billiards, for example, were Anatoly Katok and Anatoly Stepin, while measured foliations were in a focus of study of Sinai himself, of Thurston, and other brilliant people. And so all of them finished with the same notion and understood that we are pretty interested in the possible behavior of orbits of this map. Naturally, we say that 2 points belong to the same orbit if we can take 1 point and another one using this orientation preserving isometries that we defined. So once people understood that the orbits of interval exchange transformations are very meaningful from different points of view, they started to study them and immediately arrived to some simple results. So first they asked themselves, is it true that typical interval exchange transformation is minimal? Of course, you know that when we rotate the circle, if the rotation angle is rational, so it's a rational number multiplied by pi, then we will have finite orbits, while if we take an irrational number, then we will have everywhere dense orbits. So they started to expect that interval exchange transformations, as their baby examples, should be very often minimal, should have all orbits everywhere dense. And this expectation was confirmed by Michael Keane in 1975 in the following sense. So when you look at interval exchange transformation, you can describe it using 2 types of data. First, you need to know the length of intervals of continuity, these red, green, and blue guys. And then you need to know the order in which they appear on the top and on the bottom level of our picture, in the pre-image and in the image. So this is very convenient to code with a permutation. Permutation in a very simple sense, not in a sense like you do in algebra when you teach students of the first year, but in a sense that you write 2 floors of numbers. The first floor is responsible for the order of intervals on the top level. Here it would be 1 to 3. And the second floor is the one that is responsible for the order on the bottom level, 3 to 1 does. So if we assume that this permutation does not split into 2 independent parts, then we can expect that interval exchange transformation is minimal. So Keane proved the following statement, that if 2 singular points, singular means the ends of the intervals of continuity, except the ends of the support interval. If these singular points do not meet at the same orbit, at least 2 of them, then interval exchange transformation is minimal if, of course, the permutation does not split into 2 independent parts. In particular, it means that if you have rationally incommensurable length, then you are very happy and Keane guarantees you minimality. Of course, sometimes you need to deal with a more specific case of interval exchange transformations when this condition is violated. In this case, Keane's theorem says completely nothing. And indeed, there are some examples when interval exchange transformations are minimal, despite of the existence of rational relations among the lengths of the intervals, and some examples when it's not true, and much more examples when we don't know the answer of this question. So if you have some ideas how to understand when we have minimality and when we do not have it, when Keen's condition is violated, welcome on board. We will be very happy to make some progress. However, today I will concentrate on more standard interval exchange transformations, the ones that are covered by Keen's theorem. Of course, you understand that almost all of them, in the sense of the Lebesgue measures that you have in the simplex of the length, are covered by Keen's theorem. So once Keen understood that minimality is something expectable, then he posed the question, what about unique ergodicity? The first candidate for the invariant measure is, of course, the Lebesgue measure for these maps. And the question is either this measure is ergodic, and if it is a unique measure that has this property. And indeed, the typical interval exchange transformation is uniquely ergodic. It was proved independently by Howard Mazur and William Veitch in 1982, 2 papers, the same issue of Annals of Mathematics, where this fact was confirmed. Of course, almost every cannot be improved, in the sense that there are some examples of interval exchange transformations that carry more than one ergodic measure. And it happens that you have quite many of them. For example, you may have up to integer part of half of n. Then people continued to ask more and more sophisticated questions about mixing properties of this map. In particular, there is a famous result by Katok that they are missing completely the strong mixing, and the famous theorem by Avila and Forney, who proved that typical interval exchange transformation, if it's not a rotation, then it almost always has a weak mixing property. I have to admit that already in the papers by Mazur and Veitch, we did not have such a nice sufficient condition as the condition we mentioned in the context of Keen. Sorry. So here we are struggling to describe explicitly the set of parameters, the set of length, that, for instance, necessarily leads to interval exchange transformations that are weakly mixing or that are not weakly mixing. But we have examples of both types of behavior, and we know that typically they are weakly mixing and they are absolutely never strong mixing. So people continue to study interval exchange transformations. They have much more very cool results, partly because not only pure dynamists are now working on these questions. They made a very efficient union with the specialists in topology and also in geometry of modular spaces, for example. So they are progressing very fast. And for instance, some of the results of Mariam Merzakani are also in reality pretty related with interval exchange transformations, and in particular allow us sometimes to treat some specific interval exchange transformations that are not covered by this almost every condition. But as I told you, I would like to concentrate today not on interval exchange transformations themselves, because you already saw so many brilliant mathematicians who are working on them. They achieved some interesting results, but kind of interval exchange transformations are already celebrated a lot, right? So what I want to show you today is that they have many relatives, and not any of them is as celebrated as interval exchange transformations, but still the study of their orbits and their dynamical properties can be interesting and useful. So my main character for today is called interval translation mappings. These guys were introduced by Michael Bouchernitsyan and Isaac Kornfeld in 1994. You see, they are much younger than EATs, and they look pretty similar. So you do the same exercise as we did at the beginning of the definition of interval exchange transformations. Namely, we take an interval and we divide it into several parts. For instance, in my picture, we have 3 parts, 3 subintervals. And then on each subinterval, as before, we define a map, which is the orientation preserving isometry. However, now I remove the condition that in the image, the intervals that are images of our original intervals should also form a partition of the subinterval we are interested in, of the support subinterval. So what does it mean? You see some of the images can overlap, and some parts of the support interval may not be covered at all. So some points may have many pre-images, and some points may not have any pre-images. And these ITMs were introduced in connection with billiards, once again, but with rather specific billiards, so-called billiards with spy mirrors. It means that you take a billiard, for example, in the square, but it's not important, and in some polygon, and you add some obstacles that are pieces of line, and these obstacles work in the following way, that if you touch it from, for instance, from the left side, it's transparent, so your billiard floor does not notice that there was an obstacle. But if you touch it from the opposite side, then it behaves as a real component of the border, and you need to make the reflection as for the border components in a real billiard in the polygon that was the border of your table. So these billiards with spy mirrors lead us to the notion of ITMs that appear as the first return map on the transversal. So on the first glance, since they look so similar with interval exchange transformation, you can suspect that they're just the same class of dynamical systems. And indeed, many of them are, but not all of them. So we will distinguish two options. One option is the situation when after some finite number of iterations, the image stabilizes. So we define the sigma I as the intersection of the interval with its image and so on with the iterations of the image of the original interval. And so it may happen that after a while, we will stop to lose some parts, we will stop to have some parts that are not covered by any interval. But if it happens, then indeed we are in the situation when we basically have the interval exchange transformation, even if we at the first glance we have not noticed it. So these kind of ITMs are called ITMs of finite type. But it may also happen that we never get such a situation, and every time the image is as small as a proper part of the intervals that we had on the previous stage. And our image is a kind of a counter set. In this case, we call ITM to be of infinite type. And this was the idea of Bosharnitsan and Kornfeld, and they constructed the first example of ITM of infinite type, indeed, showed that it existed. But then they ran some experiments and they started to suspect that it's a very rare situation. And they formulated the conjecture that almost all ITM are of finite type. So almost all ITMs are in reality interval exchange transformations. This conjecture remains open, but it was proved for several particular families of ITMs. And that's what I want to discuss today, a little bit more in details, showing you some concrete results for these families. But in a full generality, the question is still open. And the reason why it's very hard to study is the following thing, that if we go back to the interval exchange transformations, you have such a list of cool results, and all of them were obtained due to the existence of so-called renormalization procedure. So renormalization procedure informally is a way to construct a dynamical system with a smaller support set, but which is an equivalent one to the original one in the sense of the behavior of orbits. So if the original, for instance, interval exchange transformation had finite orbits, then the new one that lives on a smaller support interval also should have finite orbits. If the original interval exchange transformation does not have finite orbits and all its orbits are everywhere dense, then we expect that the same should hold for the resultant system. And so it's a very efficient tool in dynamical systems in general, and very often the study of the ergodic properties of renormalization procedure contain a lot of information about the properties of the original system. So in case of interval exchange transformation, the renormalization procedure is a very famous one. It's called the Rosy induction, in honor of Gérard Rosy, French mathematician. While here for ITMs, if you consider the general one, we don't have any efficient renormalization that would work well for all the ITMs considered as a huge class. So we are missing some smart renormalization. And these particular families that I'm going to cover in my talk are those for which we were able to construct the renormalization in a rather efficient way. So the first family where it happened was introduced by Henk Bruin and Serge Trubetskoy in 2003. And you see it's something relatively simple. Maybe I want to show you the picture before I proceed. So the idea is the following. You take an interval, you divide it into 3 parts, and then the rightmost person, it's yellow in my picture, it goes to the leftmost side, while 2 other people, the red and the green guy, they go to the rightmost side. So their new right end coincides with the end of the support interval, with the rightmost end. So that's exactly what is written here. You see, we say that we have x plus alpha when x is from 0 to 1 minus alpha. So the 1 minus alpha will go to 1. We have x plus beta when x is between 1 minus alpha and 1 minus beta. So once again, 1 minus beta will go to 1. These 2 first intervals both go to the rightmost part, while the third person is the one that goes to 0, its leftmost end, which is 1 minus beta. We have to plus beta and minus 1, so it will go to 0. So that's exactly the picture that I showed you. And they defined such a family, and they proved the theorem that almost all members of this family are of finite type. They were able to do it because they introduced some kind of renormalization. And they also constructed the first example of non-uniquely ergodic ITM from their class. And they conjectured that typical ITM of infinite type should be uniquely ergodic. But this conjecture is not a very precise one, because as you see from their theorem, almost all ITMs from their class are of finite type. Thus, we have to deal with those who are of infinite type. And so, from the point of view of Lebesgue measure, this set simply does not exist. So we need to define some new measure whose support set will be exactly the set of lengths of intervals, the set of alpha and beta parameters in the definition, such that the corresponding lengths give rise to the ITM of infinite type. And then we should say that almost all with respect to this measure, this mysterious measure, should be uniquely ergodic. So this, they did not construct any measure, and moreover, the way how they defined the renormalization procedure does not give them many opportunities to do it. So it's not easy, because they defined it as a kind of some Gauss map, some first return map, and they did not, were not able to use standard tools from ergodic theory to proceed with it. So we improved their result a little bit recently in the following sense. Jointly with Mauro and Pascal, we showed that there exists some natural measure that lives on this set of parameters that is so exceptional that it has Lebesgue measure 0, the set of parameters that gives rise to ITM of infinite type, We constructed some natural measure who has this set as a support set. It's natural in a sense that it's invariant with respect to the renormalization procedure that we defined. And we showed that almost all with respect to this measure ITM of infinite type are indeed uniquely ergodic. So we confirmed their conjecture, but made it more specific because we posed a particular measure. We put a special measure to this fractal set. And also our approach allowed us to say a little bit more because we were able to estimate the Hausdorff dimension of this set. We showed that this Hausdorff dimension is strictly less than 2. The examples of non-uniquely ergodic ITMs from this class already existed due to Henk and Serge. So our next goals are the following things. First, we would like to understand better the fractal nature of this set. Partly our interest is motivated by the following fact. There exists another fractal, which is also quite famous in the same context. This fractal is called the rosy gasket. It also appears as an interesting exceptional set when you study some other generalizations of interval exchange transformations. And recently, the rosy gasket was very widely studied exactly by specialists in fractals and stationary measures and these kind of things. So we would like to understand if it's true that their methods can be extended to our case as well. And the second thing, which is very important, is to provide more geometric motivation to what we are doing, to relate it to the billiards, to the interval exchange transformations, and so on. So the current work in progress is on the estimations of the Hausdorff dimension, partly using the ideas with the connection of this dimension with a affine dimension, and partly using techniques that were introduced for the rosy gasket. So in order to be more understandable for you, I want to explain you how the renormalization may work in my particular case. So the idea is that we want to consider the first return map to some smartly chosen subinterval. In our case, there are two options. It depends which interval is longer. So the first case, that's the first two drawings in my picture and the arrow between them, corresponds to the situation when the red interval is longer than the yellow one. So in this case, I want to consider the first return map on the interval that is covered by the bottom red interval. So what will happen to us? Look, the green person is already there and it's mapped again to the same part that we are interested in, so the green guy would not move at all. The yellow person went to the part that now we want to cut from our interval, so it needs to use the ladder provided by the leftmost part of the red interval to go back. So that's what will happen to the yellow one. And the red interval, the rightmost part of the red interval is preserved because it's already on the set that we are interested in. And the part in the middle that corresponds to the hole between the yellow and the red interval is covered by only one interval from our ITM. So it means that if you look at the interval of the orbits of the points that are in this position, then you can simply trash them, you can ignore them, because they will not influence on the orbit behavior of the system in general. They cover the part that is empty, so they don't have images here. So we will get a new system that lives in the smaller support interval and survived in such a condition. A similar thing takes place when you look at another case, when there is a red interval which is shorter and yellow which is longer. If you are tired and lost at this moment, don't be stressed. It's not so important. It's mainly maybe interesting for those who played a similar game with interval exchange transformation. But in case if you have not played yet, then just try to understand that it's something very natural, because it's a first return map on some subinterval that we choose smartly, and that we can visualize it very efficiently. And then what it means that in order to explain what happened to the ITM, we need to specify two things. We need to know in which order the intervals of different colors appear on the top level. It could change, and that's what happened to us in the second case. And we need to know their new length. And the lengths, they have the following destiny. I wrote it here. So in the first case, we have the situation when A is the length of the red interval, and the red interval was so long that it was longer than B plus C, so it was longer than 1/2 of the support interval. In this case, we have to subtract the sum of B and C from A, and then there will be B and C preserved. The second option was when, as on my picture, A was smaller than C, and in this case, A and B will be preserved and C will be replaced by C minus A. And there exists one more option if we were in between C and B plus C, but it's quite easy to see that in this situation, we will be in the case when in reality we can reduce our ITM on 3 intervals to the ITM on 2 intervals. And there is another exercise which is very easy, and everyone can do it immediately, that if you have ITM on 2 intervals, it's always of finite type. It's always an interval exchange transformation. So to put it short, that's the renormalization that we have. And if we have some specialists in multidimensional fraction algorithm in the auditory, they probably are already quite curious, because they see features of some famous algorithms in these algorithms that we just produced, because the first line looks pretty much like Arnoux-Razi multidimensional fraction algorithm. And that's what was studied in connection with the rosy gasket that I mentioned already. And the second line looks a little bit as a line from the description of Cassain multidimensional fraction algorithm that was recently studied by Julien Cassain, Sébastien Labbé, and Julien Leroy. So it looks like our guy is a mix of 2 famous multidimensional fraction algorithms. If you want, he's a son of a couple, where one is the Arnoux-Razi and another one is Cassain algorithms. So this guy has the features of both. So from the point of view of the study of Markovian multidimensional fraction algorithms, he is also very interesting. Now I want to show you how the fractal looks like. So what we are doing is that at every stage we have to remove the part when we had this condition violated. So when we have A between C and B plus C, this part should be removed. And what remains gets kind of smaller and smaller, because at every moment you remove somebody. So that's how this fractal looks like. Those who have seen the rosy gasket can notice that it's a very similar but different gasket. So the next point in our research project was about weak mixing properties of these maps. And this question is apparently very exciting one, because we get some kind of results that slightly contradict each other. And it doesn't happen for us when we are working with interval exchange transformation. Namely, Henk Bruin and Sarah Radinger showed that typical ITMs of infinite type from the Bruin-Trubetskoy class are weakly mixing. As in the paper by Henk and Serge, they don't explain what does it mean to be typical, because they don't know how to put the measures there. We know in our theorem, but we have not published yet, and so our colleagues do not know. But they provided a proof for some particular examples, and this proof is based on the study of the eigenvalues of substitutions that are associated with so-called self-similar ITMs. Self-similarity means that you consider a first return map to some subinterval, and you get the scaled down version of the original system. So you can iterate this process, and you always will have a scaled down version of the original system, more and more scaled. And so, of course, you will have uniquely ergodic guy, and they show for some examples that you will have the weakly mixing one. At the same time, Mauro, Pascal, and me, we showed that the renormalization algorithm defined above, this algorithm, is almost never weakly mixing. And this follows from the study of the Lyapunov exponents of the associated cocycle, and we partly replicated the strategy suggested by Julien Cassagne, Sébastien Labbé, and Julien Leroy in the context of the Cassagne algorithm. So we get a little bit strange situation when the renormalization is not typically weakly mixing, while all the examined examples typically are weakly mixing. And the question about the behavior of ITMs in a full generality, if it's true or not that almost all with respect to our measure are weakly mixing or not, this question remains open. Maybe I should say a couple of words also about how we proved our theorem, the one that is written here. And we should thank for that Jacques Fougeron, who wrote a very impressive paper some years ago about the properties of multidimensional fraction algorithms and simplicial systems. Namely, once we defined the renormalization and found our algorithm, it was a technical question to check that our algorithm is good from the point of view of Charles' paper and satisfies all the technical conditions that are formulated in this paper. And then both the estimations on the Hausdorff dimension and unique ergodicity followed immediately from Charles' result. So the second class for which we achieved some interesting observations is the double rotation. The double rotation is slightly different thing. It's not an interval, but it's the map. Sorry, it's not a map on the interval, but it's a map on the circle. And this map works in the following way: that you add alpha to y if it's from between 0 and c, and beta if it's between c and 1. So I missed the picture. I apologize for that. But it's relatively easy to imagine if you like to consider maps on the circle. You just divide your circle into two parts and you rotate one part on one angle and another part on another angle. And if you prefer to live the life on the interval, then you do the similar thing, just since we divide it on the circle. Sometimes one interval can split in two parts. One part will live at the rightmost part of the support interval, and the continuation will be at the leftmost part of the support interval. So the first renormalization for this class was suggested by three Japanese mathematicians, Suzuki, Ito, and Aihara, in 2011. And later Hank Bruin and his student Greg Clark successfully used it to establish the proof of Boshornitsan-Kornfeld conjecture in this particular case. And once again, they formulated the conjecture that probably there should be some way to construct the measure that would have as a support set the set of the parameters that give rise to the ITMs of infinite type. And they even got an idea that it should be somehow related to thermodynamical formalism, but they did not provide any construction. And also they posed the conjecture that probably typical representatives should be uniquely ergodic. They proved some kind of conditional theorem saying that if there exists such a measure that is invariant under the renormalization and has the interesting set as a support set, then with respect to this measure, almost all maps should be uniquely ergodic. So in 2021, Mauro, Pascal, Fougeron, and myself constructed another renormalization that looked much more as a renormalization we have in the world of interval exchange transformations. It was very similar with the Rose induction. And we used this renormalization to provide the simplicial system. We got some kind of multidimensional fraction algorithm again, and we were able to check that it's good from Sharp's point of view. It's covered by Fougeron's criterion for simplicial system. And so we a little bit improved their results in the way that I stated. So the set of parameters that give rise to the double rotation is strictly less than from the point of view of Hausdorff dimension, is strictly less than 3. And there exists a measure that has it as a support set. It's invariant with respect to our renormalization. And the ITMs are of infinite type are uniquely ergodic with respect to this measure. I have to say that we don't know any examples of non-uniquely ergodic double rotations that are not from the class of Bruin-Trubetskoy map. So it doesn't mean that they do not exist. It just means that we were not able to construct them. And those who are of Bruin-Trubetskoy class, they are, of course, degenerate from the point of view of double rotations. The question of weak mixing is not studied at all. There are basically absolutely no interesting results and observations. So it's a complete green field where we are supposed to contribute. And before I arrive to the main slide, the most interesting one, and allow you to listen to a real talks, not to a virtual one, I want to comment on another aspect of study of these ITMs. Namely, I would like to say a few words about their symbolic dynamics and combinatorial complexity. The point is the following, that when you look at the dynamical system, like for instance interval exchange transformation, let me go back to our picture, there is a very natural way to associate a symbolic system with it. Because instead of enumerating the intervals, we for instance could give the names to them, for example, according to their colors, G, R, and blue. And then we could, red, green, and blue. And then we could code any orbit by words that are built with these letters, with these colors that we gave them. So the point can be on the red boy, then it could go to the green one, and then from green, for instance, it goes to the red one again, and then it goes to the blue one, and so on and so forth. So we can look at it, and we can ask ourselves a very natural question. How many words of the length n we may have such that they will code some orbits of a given interval exchange transformation. And for interval exchange transformations, the answer is noun. Namely, there is a precise formula if the interval exchange transformation satisfies Kin's condition. We can show that the complexity is linear, and the formula is d minus 1 times n minus 1, where plus 1, where d is the number of the intervals of continuity. In particular, if you have just 2 intervals, you will have complexity n plus 1, and you will have so-called Sturmian words. Then if you remove Kin's condition, you will need to give up with the idea to get a precise formula, but you can have an estimation, and still you can show that your complexity will be sublinear. In case of interval translation mappings, the situation is much more delicate. And in the full generality, it's still the open question. Nobody knows the answer. And for the case of Bruin-Trubetskoy, Julian Cassagne obtained a linear estimation. It was a very complicated and hard proof. Recently, my student Valentin Chorny generalized it to the case of Bruin ITM. They are those when you define them in a similar way, like here, but you consider some abstract number of intervals. So you can get as many intervals as you want, and all of them but the last one go to the rightmost end, and the last one goes to the leftmost end. So it's still linear. But for double rotations, precise complexity estimations are not known. There were some partial results due to Greg Clark and his thesis, but they were not published in any paper, and basically we cannot say anything except the obvious fact that the complexity should be at most polynomial, but we don't know if it's linear or non-linear. And one of the reasons why do we care is because, okay, it just gives us some new information and some new examples of geometrically meaningful symbolic systems. But at the same time also, you know, it can be used also to study ergodic properties because, for example, here we don't have any efficient estimation of the number of possible ergodic measures. And for systems with linear complexity, there are many. This work was initiated by Boshornitsan and recently continued by Damron and Fickenscher. So the linear estimation would allow us to proceed with some interesting conclusions in ergodic sense as well. So I think that's all I wanted to tell you today. I tried to be quite fast because I know that it's very annoying to listen to the virtual talks at the real conference. So grazie mille, thank you for your attention, and sorry again that I'm not here in person with you to discuss it in a more convenient way. Thank you very much for your attention.
Yeah, thank you very much for your talk. It was great to see it, even if it's online. Are there questions? I'm walking. It's coming.
Being so far away. Hi, Sasha. So that's nice to see you. So my question was about the Arnoux-Cassaigne algorithm. So do you have some estimates on this Lyapunov exponents and the behavior? Is it strongly convergent, something like that, or?
Yes, I think we do have the same estimations. Kind of what we are able to prove is that the Lyapunov spectrum is simple.
Okay.
And that the Piecewise condition is satisfied almost always.
And also for finite products, are they Piecewise or?
Yes, I think so, that they are Piecewise. I think we have just the same result as Sébastien, Julien, and Julien have in their case.
And is it what you use, this kind of property, for what you use from them to
we don't use it from them because it's a different algorithm. As you see, it's a mix, so we need to repeat their strategy.
Oh, so, yeah, I understand, but I mean, this is the information you need to be able to prove your result on weak mixing.
Yeah, exactly.
Okay.
Of course, we use also the result by Valérie Berthet, Wolfgang Steiner, and others to conclude that in case of Piecewise property, we don't have weak mixing. So we used the estimation on the Lyapunov exponents. But the delicate point is that you see it's a result for the multidimensional fraction algorithm, but it does not mean that the same necessarily holds for the ITM itself. If you want, it means that what we proved with Maurer and Pascal is that the suspension flow that you construct naturally, like you do suspension for systems of isometry, that the suspension flow is almost never weakly mixing. But then you see the particular section of the suspension flow at the same time can be weakly mixing.
Thank you. So by the way, I was Valérie. I don't know whether it was clear for you because I
understood.
Okay.
Salut.
Other questions? I have to look very carefully. So in what you said last, you mentioned that you could do this Bruin-Trubetskoy example also with more intervals to the left. So does it change if you do intervals both to the right and to the left? Does that make things a lot more complicated, or?
Yeah, it makes, because the renormalizations that we define, it stops to work. So this renormalization that I showed you, you see, it allows us to stay in the same class. So I started with the guy who was in the Bruin-Trubetskoy class, and I finished also with the picture that is in the Bruin-Trubetskoy class. But if I increase the number of intervals in a way that all of them go to the right except the one that goes to the left, or you switch, but you understand if you have this, that only one person goes in the opposite direction with respect to others, and this person is the one that lives at the very end. So that's what Hank Bryan described in his separate paper without search. So if I'm in this Bryan class, I still can do my induction. It will be exactly the same, and I can do the similar things as we did, as I explained today. But if I consider some more general picture, my induction kicks me out from the class. So for instance, if like I consider 4 intervals and 2 go to the right and 2 go to the left, I start to apply it and I get the ITM where this condition is not satisfied anymore. We don't have the situation when 2 go to the right and 2 go to the left. We get some different type of ITM. And what is hard is to show that if we iterate long enough, we will be back to our class. And this we miss completely. So that's why we don't have renormalization for any other class except Bryan-Trubetskoy and the double rotation and Bryan himself. That's it.
Okay.
Like if one introduces a better renormalization that will not kick us out from the class, it will lead us to more interesting observations.
Thank you. That was clear. Yeah. Moving. Another question.
I have a question about the fractals. Do you have any ideas of like what the dimension might be or lower bounds at all?
Well, we don't have, but we are working on it right now. So the upper estimation, you know, for Rosy gasket, there is a paper by Marc Policot and Ben Sewell, and they have 2 papers apparently. One where they improve a little bit our estimations that I made with Pascal and Arthur, where they have like 1.97. And then there is another one where they go very close to the estimations that you get at the computer. So in our case, my student Kirill Zernikov was able to reproduce their strategy for the fractals that I was talking today about, and to get something like 1.97. But the idea to repeat their strategy and to adapt it, the strategy from their second paper when they are getting a better estimation, this is still work in progress. And concerning the lower dimension, we are trying to do what people did very recently when they showed that affine dimension and Hausdorff dimension should coincide, and to estimate affine dimension in the case of our fractal. But this is still work in progress. I'm not able to provide any numerical estimations. But I hope that thanks to our very smart colleagues who stick to the Rosy gasket, we would be also able to get something for our fractal as well.
Thank you.
But I don't know the precise number. I mean, I have no idea how to interpret it. What number it is. It's very interesting, of course.
Any other questions remaining? No? So if not, then let's thank Sasha again for a very lovely talk.
Thank you very much. I'm very impressed that after Italian lunch, some people came to attend my talk, even online. Thank you very much, and I really hope to be in person next time. Grazie mille.
Thank you very much. And then it's time to start the next talk. So next speaker is Rose Elliott-Smith, who will talk about measure rigidity on u-Gibbs states.
Hello?
Please go ahead.
Is this good? Yes, you hear? Yeah, okay, good. All right, thank you for the opportunity to speak. So yes, I will speak about measure rigidity of a certain class of measures that are relevant in usually partially hyperbolic systems, but we're going to talk about just in general where you can define these things. I should say 2 caveats before we get started. The first one is this is still work in progress. I hope that the preprint will be up by the summer sometime, but you never know with life. The second one is that most of this talk is measure theory. So take your topology and just like put it in the seat next to you. When I say that there's a splitting, I mean that it's a measurable splitting. I'm usually not talking about topological splittings. This is actually quite important because you you can almost never ask for like nice continuous splittings in the settings we're talking about. So just keep this in mind as we go through it. It's all measure theory. Okay, so let's get started. So for the duration of today, this is our setup. M is a closed Riemannian manifold. I'll give examples in dimensions 2, 3, and 4 usually, but in principle, this stuff will all hold in any dimension. We take some smooth diffeomorphism that's going to be the object of our dynamics, and we take mu to be an F-invariant Borel probability measure. Usually, again, we'll ask this to be ergodic, but not necessarily in advance. And then we're interested really in how mu and the Riemannian volume on M, which we'll denote by little m, interact. So that's really the goal, is how can we understand the regularity properties of mu with respect to M, our volume? Okay, so going through the talk, we're going to have one example that'll carry us through. Megan already mentioned it, but this is the cat map. It's a map of the two torus. It acts by that matrix. It has a lot of nice properties. So these are its eigenvalues and eigenvectors. It's not really important what they are. The point is that it has one that is greater than 1 and one that is less than 1. So this tells us it's uniformly hyperbolic. So it's an Anosov, and it's going to have all the nice properties that we could possibly want for the duration of this talk. So what does it do? Well, this is our torus. This is a loop on our torus, and the cat map takes this loop to this one. So it stretches in one direction and shrinks in the other, just as we would expect. So going through the talk, keep this in the back of your head, though it'll be very helpful for a lot of examples. Okay, so our motivation. So the motivation of this talk is we want to understand orbits. And how do we understand orbits? Well, given a series of points, x, fx, f2x, etc., we can ask, what can we build on this set that actually gives us an understanding of the properties of our orbit, especially in the long term? And the answer is we can build measures. So again, this is something Megan mentioned, but we can build on an orbit what's called an empirical measure that is just the average of points along our orbit. And then we can do this for any n, and any weak star limit of such a measure will be F invariant. So this tells us that on any orbit closure, we can build an invariant measure. So to understand orbit closures and to understand the statistical properties of orbit closures, a very good first step is what are the invariant measures of our system? So this is the key motivation. Measure classification has like so many applications and uses. It's a really, really rich field. But in specific, for the purposes of this talk, the motivation you should have is we want to understand orbit closures. Measure classification and rigidity tells us about orbit closures. Okay. Now let's get a little bit more specific. So if I give you an invariant measure, you can define this object called the basin of mu. The basin of mu is all points where mu governs its long-term behavior. So if you build this empirical measure that averages along your orbit, it limits to the measure mu. Now this tells us that mu gives you all the information you could possibly need about every point in its basin. So a really simple example, if we have a fixed point, then it is in the basin of a point mass on the fixed point, right? The fixed point will give you all the information you need about the fixed point. But of course, this basin could be much larger if it was an attracting fixed point, and it could be only that if it was a repelling fixed point. So a priori, you don't know exactly how big such a thing is. But we can ask a very logical question, which is, well, okay, if we don't know how big it is, how can we measure how big it is? And one answer is we can say that if it has positive Lebesgue measure, if the basin has positive Lebesgue measure, then it is what we call physical. These objects are very interesting because in some very intuitive sense, they describe what happens to the majority of stuff on our manifold, right? If I tell you, like, you have 5 physical measures and their supports cover, or their basins cover the whole thing, then you know everything about almost every point on your set. So it's a very useful classification. So we want to understand physical measures. So going back to our example, if we look at the cat map, Lebesgue measure on our torus is the unique physical measure. And this tells us that almost every point with respect to Lebesgue has a dense orbit. So what does that look like? We take a point, we iterate it, we have a nice equidistribution property. So again, returning to orbits, physical measures tell us a lot about the orbits of large sets. Okay, so the core question of today is this: when is mu physical? Now, there are a lot of different answers. This is very well studied, has a long and rich history. In particular, if F is a Anosov, which means uniformly hyperbolic, and this is topological, I promise, then we know that there's a finite set of invariant measures, invariant physical measures. And we call such measures SRB for Sinai, Ruel, and Bowen. So if we have Anosov things, then we know physical measures exist. And the point of today is we want to loosen that. If we don't have something that's Anosov, what can we say about physical measures existing? In general, the answer is you can say nothing. Like, you don't really know. You don't have a good understanding. But in certain settings, we'll have better understandings. So again, returning to our example, as before, the cat map is Anosov. So it has a finite set of invariant physical measures, and in fact, it just has one, and it's mu. Okay, so we're going to need a little bit of technical tools before we get into sort of the meat of the theorem that I'll be talking about today. So I'm not going to linger too long on this. We've all seen this before, and many people today even talked about it. But we have, the multiplicative ergodic theorem. In particular, just notice that I'm going to call our Lyapunov exponents lambda 1 through lambda n. I'm going to assume ergodic so that I don't have to worry about what these are dependent on. And then again, in terms of our example, for the cat map, our Lyapunov exponents are just log of our eigenvalues. So really concrete things here. So if we take curves along our manifold that are, tangent to, tangent to, our first Lyapunov direction or our second Lyapunov direction, we can understand exactly what happens to these. And what happens is they get stretched in the E1 direction and shrunk in the E2 direction. So these curves are little pieces of our local stable or unstable. And in particular, just remember that zero exponents are the enemy for this talk. They don't show up too much, but in general, we can really only say things when we have positive or negative. Okay, so with all that said, going forward, we assume that we have positive top exponent and negative bottom exponent. We are not yet eliminating zero exponents in the middle. So everything up until a very specific point, we could have zero exponents. And we assume mu is not hyperbolic, ergodic, and we call such a thing partially hyperbolic. So again, this is not in the topological sense, this is just a measure theoretic statement. Then we have our Oseledets splitting, and we're going to do something a little strange. Well, not strange a priori, but strange in how we do it. So in general, you can group up your Oseledets splitting into directions of growth and directions of shrink, and then something you leave in the center. This is very common, especially when you're talking about like a partially hyperbolic diffeomorphism. But the difference here is that this splitting is measurable, and I'm not putting everything in the unstable. So I will, in general, take all of the negative exponents and put them in the stable, or what I will call the strong stable. And I will put some number of the positive exponents in the strong unstable, which is EUU. But the center direction could have zero exponents, but it can also have positive ones. And so this isn't like I just took all of the positive ones and put it in the strong. I'm still leaving things in the middle. And the reason for this will become clear. So if you give me such a thing, we can build our familiar unstable manifolds. So the strong stable is tangent to a lamination, the strong stable lamination. Same thing with the strong unstable. There are, of course, some measure theoretic words here that I'm going to ignore for the sake of technicalities. But in general, we have some nice foliations. So given nice foliations, this is a piece of what they would look like. So we have our strong unstable direction. Now we have a measure and we have a foliation. So the next logical question to ask is, how does the measure behave with respect to that thing, right? So we want to disintegrate our measure along this foliation. Now, in general, this isn't something we can do because the measure or the foliation is not necessarily measurable. But you can get around this technicality and build things that we're going to call conditional measures. So along each of these leaves, we build something called the strong unstable conditional measure of mu at x, which is a mouthful, bear with me. And it has the properties that you would want it to have. So it's supported on your leaf. And for any measurable function, integrating across the whole manifold is the same thing as integrating across a leaf and then over the set of leaves. So it has the properties you would expect. Now, if you're not familiar with conditional measures, the way that you should think about this is like this. If I take Lebesgue measure on a square, and I want to understand how it behaves on all vertical lines, I can construct conditional measures where I disintegrate Lebesgue onto the vertical lines. What do I get? I just get like Lebesgue measure on a line, and I get that for each line. So conditional measures is really just a way to take your measure that's defined on some larger space and break it down into smaller pieces and hopefully leverage that to gain some understanding. All right, so again, as mentioned, the center direction could have positive growth. If it does, we can construct another foliation, which we will call the weak unstable and denote WU. And on such a thing, we can also define, yes, question? So it contains all. So yeah. Otherwise, it wouldn't foliate. Yeah. Good question. Yeah. So then we can define mu u the same way. So we can again disintegrate because it is a foliation because we've included the top ones as well. Okay. So there's one last kind of technical object that we need to understand before we move on to defining things, and that is jointly integrable. So again, something Megan mentioned. But we can ask the question, all right, so the strong unstable is tangent to a foliation. The strong stable is tangent to a foliation. The weak unstable is tangent to a foliation. But what about if we take the strong stable and the strong unstable and put them together? Is that tangent to a foliation? And that question in general is hard. Like this is not an easy thing to answer in most systems. And if it does happen, we call this system jointly integrable. So what does that actually look like? Well, if we have our little picture, these should be local. All of these, just put local at the bottom. So if we have this sort of local picture of the strong unstable of X and the strong unstable of, and the strong stable of X, what joint integrability looks like is a box closes. So the picture you want to have in your head is we can walk along the unstable and then look at a stable, and we can walk along the stable and then look at an unstable, and they'll intersect at just one point. So again, the picture I always have is you have a box and it closes. Now, why does this actually tell you that these objects are going to be tangent to a lamination? Well, what it tells you is you can construct some mesh. Like you can construct a mesh that'll define, I've drawn these as one-dimensional, so it'll define a surface in this case. And that will be what your foliation actually looks like. These are the leaves of your foliation. So joint integrability says you close a box and that box lets you build a surface. Or in general, a higher dimensional submanifold, whatever. Okay, so let's return to our question. When is mu physical? So the approach for today is study what are called u-Gibbs states. So again, I have to tell you what this is, but luckily we now have all of the actual information to define this. So we say mu is u-Gibbs if its if its conditional measure with respect to the strong unstable is absolutely continuous with respect to the Lebesgue's conditional measure with respect to the strong unstable. So the tagline you want to have in your head is it's morally volume. So along the unstable manifolds, it looks like the volume on your manifold. And again, this makes sense because what we're after is physical measures. Physical measures are somehow very related to volume. So defining an object that is again related to volume, it makes sense. Now we're similarly going to say that mu is SRB if its weak unstable conditional measures are absolutely continuous with respect to weak unstable conditional measures of volume. So I should mention, this is not a standard definition. In particular, if I have 0 exponents, this measure will not even be physical. So keep in mind, very unstandard definition. But if I do have no 0 exponents, so if there are no 0 exponents in my system, then this definition of SRB does give you a physical measure. So if we have no 0 exponents and we have this condition, then we know we have found a physical measure. And that's the point of the whole talk, right? We want to find physical measures. How can we find them? We can find them with this. So the game we're going to play is increase the regularity from being absolutely continuous with respect to a restricted set to a bigger set. That's the goal. And it's worth mentioning that if we have a partially hyperbolic diffeomorphism in the topological sense, then it has at least one u-Gibbs measure. This is known. But in general, it could have an infinite number. It's not really well understood just how big that set could be. Okay, so let's do an example. So this first map is, again, our cat map. Remember, it's hyperbolic. The second map is just another toral automorphism. The only things you need to know about it are it has bigger eigenvalues than the other one, so it has stronger hyperbolicity, and its eigenvectors are different. So really the goal is we want an Oseledets splitting that's 4-dimensional, and we want its eigenvalues to be bigger. So with this, yes, both maps have volume as their unique SRB measure, because again, they're both Anosov. So with this, we can construct F cross G on our 4 torus. And we're gonna do our sort of strange grouping. We're going to put the unstable of F in the strong unstable. We're going to put the unstable of G in their center direction, and we'll just put both stables in the strong stable. So the key point here is that we've broken up the growth into the center and the strong unstable, but we've left all of the contraction in one place. So with respect to this splitting, the Lebesgue measure on 1 torus across the point mass at 0, which is a fixed point, is u-Gibbs, but it is not SRB. And then Lebesgue cross Lebesgue is SRB. So the fact that Lebesgue cross Lebesgue is SRB, that's pretty obvious, right? If you take volume, then if your measure is an Anosov and it preserves volume, then volume is going to be its SRB measure. The fact that this top one is u-Gibbs but not SRB is a little bit more subtle, but the image you should have in your head is this. I have some invariant torus in the support of my measure in some sense, right? This measure is only built on one of the tori, and it's supported on a point on the other one. So it's really, this is a statement about having an invariant substructure in your dynamical systems that you've built a measure on. If you can do that, usually, you have something that's u-Gibbs, but not necessarily SRB. Okay, so these are examples. We'll return to these later. But now let's actually get into the statement of the results. So this is going to be our motivating theorem. Again, mentioned by Megan earlier, stealing all of my content. So this is a theorem by Brown, Eskin, Philippe, Rodriguez, Hertz, and it was proved by Katz in 2023, but only in dimension 3. And this paper is very long. It has a lot of different parts, so we're focusing in on just one part of it. And the key part is this. So there's words here we don't know yet, but what you want to think is this. If we have a u-Gibbs state with some nice properties we can ask for, then it is SRB. And in particular, these properties will guarantee that it is physical. So this says if we have a u-Gibbs state with properties, we have a physical measure, which answers the question of what we were looking for the whole time. So let's really briefly talk through these properties. So partially hyperbolic, we already know what that is. Generalized u-Gibbs state. So this we're mostly going to ignore. I'm going to make one comment about it, which is that essentially a u-Gibbs state, we talk about how it's defined with respect to the very highest growth, so our strong unstable, or some percentage of strong unstable down. But you can actually, this is very technical, but you can actually pick like the second Lyapunov exponent if you want. And you can talk about, you can make sense of a definition of what it means to be u-Gibbs with respect to the second exponent, if that is also growing. And that is what a generalized u-Gibbs state is. There's a lot of technicalities that go into that, so I won't get too into it, but that's the idea. Now, no zero exponents, we know what that is. The Q and I property, this is the big one. So Q and I stands for quantitative non-integrability. We'll get into the details in a minute, but the core point is all the rest of this is stuff we can ask for pretty reasonably. So we need to understand what Q and I is. And that is the content of my work. So this was first proved by Eskin, Potri, and Zhang in 2023, and it's the subject of my work. And this says that either, so if you have something that's u-Gibbs, either you have Q and I, or you are in some sense jointly integrable. So this bottom condition we're going to talk about a lot more. But the core piece is you have Q and I, or you have this joint integrability. And this joint integrability type thing is much easier to work with than Q and I. So put together, these two theorems say, if you don't have this joint integrability condition and you have a u-Gibbs measure, you must be physical and no zero exponents. You must be physical. So this is the pathway to answer the question, when is mu physical? Now let's stop and talk about some pieces of this. So first of all, I am lying to you in the statement of this. So you don't actually get to use the full unstable and stable foliations. You have to use the stable and unstable supports of mu. So this ends up being a little bit hairier. I'm going to mostly avoid it by talking only in dimension 3, where the two things will end up being the same. But just know that in higher dimensions, you have to deal with nastier things. And the other thing is, you don't actually need a u-Gibbs state. So this theorem holds true if you just ask for some niceness properties about your measure. And the niceness properties are basically about its support. So, if you have a u-Gibbs state, it says that it's absolutely continuous with respect to volume along the unstable. This tells us that the support of that thing has to be full support along the unstables, right? It can't be absolutely continuous with respect to volume if it's not. So it tells us something very nice about the support along the unstable. So you can replace u-Gibbs with some niceness condition about the support. Okay, are there any questions about this before I get into the words? Yeah. Yes, we're going to get into that in 1 second. Yeah. Other questions? Okay. All right, yes. So what is joint integrability to order L? So it's a little complicated. So I'm going to put the definition on the board, and I'll talk through it briefly, but for the sake of time, we're going to quickly default to a picture. So in 3 dimensions, joint integrability up to order L says, at every point, I have a surface, and for that surface, my stable and my unstable are inside it. And then if I try to close the box like I would for joint integrability, I can up to Taylor expansions of order L. So the box closes, but only if you use approximations. This is the idea behind joint integrability to order L. So what is this in pictures? So this was our joint integrability picture. Joint integrability to order 2, let's say, is this picture. So instead of the actual curves, I look at Taylor approximations, and I say, oh, my Taylor approximations intersect. And so I have some like weird quadratic surface, in this case, that lives in my manifold. Now, caveats here. This is only defined for every point. So this isn't actually a true foliation because I'm getting different ones a priori. I could get different ones at every point. And the other caveat is that like these things are only tangent to order L. So, my stable and my unstable for X are contained in them. But as soon as I try to move out a little bit, I can't necessarily guarantee that the other curves are actually in this like quadratic manifold. Yeah. No, not a priori. No, they're not. Yeah. So they can be very nasty objects. And it's actually an open question of, if I have something that's jointly integrable of all orders, is it the same thing as joint integrability? So personally, I think this is true, but there are no known examples. There are no known counterexamples, and no one knows how to prove it. The rationale for why I think it should be true is something like, if you have joint integrability of all orders, you should be able to kind of take some limiting set of charts, right? You're taking a Taylor approximation. It kind of makes sense to think that you could combine your approximations as you move up, but then you still do have to deal with the lamination issue where you have a different one of these at each point. So it gets very technical. Let me not linger on this anymore. But yeah, so unknown if these two things are the same. So now let's talk about Q&I. So this stands for quantitative non-integrability. I'm doing us all a favor and not putting this on a slide. The definition takes about a full page and has enough quantifiers to make like an analyst cry. So we're not going to do it. Instead, let's do the picture. So the picture is this. The box doesn't close, and it doesn't close by a bounded amount. And this bound is uniform across your whole manifold. Of course, there are many caveats here, right? This only works on a set of large measure. You need certain actions under the dynamics, et cetera, et cetera. But the core intuition is the box doesn't close, and we know by how much. So the statement of my theorem is Q&I is the opposite of joint integrability for all orders. But again, like I said, we don't know if that's the same thing as joint integrability. So these 3 concepts are all very linked, but the relation between the 2 on the left is not well understood yet. Okay, so let's do an example. So these are our 2 things that we talked about earlier. Now, adding to the 2 theorems that I put up together, we should know that we should be able to show that Lebesgue cross the point mass at 0 is jointly integrable. And hopefully, we show that Lebesgue cross Lebesgue has Q&I. Now, in this case, this will actually just be very easy because these maps are analytic and they're actually just jointly integrable. So, or the top one is just truly jointly integrable, not jointly integrable up to order L. So we have eliminated a technicality. So if you look at the support of this measure, right, what does it look like? Again, it's only supported on the left torus. On the right one, it's just a point. And on the left one, we have our normal mesh. So it is jointly integrable, because our normal mesh on the left torus is just going to give us the whole torus. And that gives us the lamination that we would want. Now, the other one, it looks like this instead. So for this one, we have on the left torus, we have what we would want. But on the right torus, we have a piece of the stable. And this is the problem, because we can't move along the unstable and get anywhere on the second torus. We're fixed. So this has Q and I, because moving along the unstable can never get us to intersect with the movement along the stable on the right. So somehow there's this gap, and the gap comes from the fact that the unstable just can't actually move us on the second torus at all. So this is the core image. Yeah, good on time. So I'll wrap up here, but this sort of tells us that we can apply these two theorems and show that, yes, indeed, the measures that I gave you as examples, the first one is u-Gibbs, but not SRB, and the second one is SRB. Of course, we already knew that by other techniques, because those two are very easy to compute. But this is the machinery that goes into this process. Okay, thank you. All done.
Thank you very much. Are there questions? Yeah.
Okay. What do you know about the support of mu in with respect to Lebesgue measure, the basing of mu with respect to Lebesgue measure in higher dimensions?
So you mean like the stable?
Right? The basing.
The basing in general. So in higher dimensions, that's hard to answer. So if it meets the criteria, then of course it's physical, so you know it's positive. If it doesn't meet the criteria, I have no idea.
What about your question? You don't know whether there's a counterexample.
Oh, these two? Yeah,
yes.
yeah.
What's your intuition? You said.
So my intuition is first that if your map is analytic, it should be easy to show they're the same thing. I haven't actually worked through the examples, but really the
But your guess is it's jointly integrable on the whole support.
Yes, yes, yeah. So my guess is that joint integrability for all orders will be the same thing as jointly integrable when you are analytic. In general, I think it should be true for just any map, but I couldn't put my finger on exactly why.
Thank you. Nice talk.
Thank you.
Any other questions? If not, then let's thank Rose again. Okay, I think we should start with the afternoon session. So our first speaker is Igsyl Domínguez Calderón, who will talk about non-hyperbolicity of fiber dynamics. Please.
Hi, everyone. Thank you to be here. Thank you, the organizer, for the opportunity. Well, I'm going to talk about non-hyperbolicity of fiber dynamics. Well, I guess that everyone here knows the famous Fatou conjecture. And if not, let me present it to you. And elegantly says, a quadratic family of maps from the complex plane to itself is hyperbolic for an open-end set of parameters. In simple words, imagine that in this little box, we have all the quadratic dynamical systems. So, and we pull one hand and get one out. Fatou believes that if we did this without a look, it is most likely we're going to obtain a hyperbolic map. And if we have the bad look to get one that it's not, well, it's a very close one that it is. So try your luck and get your dynamical system. But can you take one and pass the others? Yes. So this conjecture is important for quadratic dynamics because the hyperbolic polynomials are very cool. Well, why? Because in hyperbolicity, we have two things. We have only attracting cycles in the Fatou set, and the Julia set has zero measure. So these properties are not only exclusive for the complex case. In general, hyperbolic systems are cool. So our ultimate dream will be that if all or almost
or at least most of the systems in that box, were hyperbolic. So another way to asking this is, how robust are the hyperbolic dynamical systems? Well, when talking about robustness, we're talking about a density problem. So, and it is known as, and it is known when we work in mathematics that we start with the simplest case, and from this, things generalize. So in here, the simplest is the linear case, where everything is already done. Then the quadratic case, etc., etc. Well, for quadratic dynamics, we have the following. From real dimension 1, this is reduced to the study of the logistic family, where Lyapunov, Gasek, and Swatek prove the density of hyperbolic quadratic polynomials. For complex dimension 1, it's exactly the Fatou conjecture. And here, we have a geometric interpretation concerning to another start of dynamics that is the Mandelbrot set. Well, what I do in this part is to study this family, set square plus c. And as you can see, this little innocent form exhibit a wide variety of interesting phenomena. In fact, this innocent little form turned out to be not so innocent because the conjecture is still open. So if you don't have nothing to do and you prove the conjecture, please send me an autograph and fame and glory. Yeah, sure. So this conjecture is strongly related with another famous one, that it is the so-called MLC conjecture, the Mandelbrot sets locally connected. Why? Because MLC implies density. So let us now travel to the complex world of dimension 2. Here appears Bussard, who shows that also hyperbolic systems are structurally stable, they are not dense. Well, all of this is really, really interesting, but what I will tell you today is doesn't live in one dimension dynamics, nor in high dimension. It's kind of an intermediate dimension, which is a type of a skew product, and that we would call hybrid dynamics. Well, what is new about the results is that the tools that we use are simpler than the ones used by Bussard in higher dimension, and even uncomplicated than the ones used by Lyapunov and others in dimension 1. So the idea is to show that in an intermediate dimension, we don't have the density of the hyperbolicity. So how we define these hybrid quadratic polynomials? Let us consider a compact set T and a continuous function on it. We are going to define the hybrid holomorphic polynomial as a continuous map from the fiber space T cross C. So this is hence by the name of skew product for this reason. For the first coordinate, this depends only on the basis space. And the second coordinate, we have a complex polynomial whose coefficients depend continuously on T. So the dimension of the hybrid polynomial will depend on the dimension of the basis space. In this case, we're going to work in dimension 1. And they look more or less like this. Then we have a polynomial dynamics. On each fiber, the action is the polynomial. but it moves along the fibers depending of the shape of the continuous function phi. Well, in his doctoral thesis, Olivier Sester studied these little things and generalized the concept and the classical notion of Julia set, Green's function, and the principal cardinal of the Mandelbrot set in the corresponding parameter space. Then, for fibrate polynomials, we need the following definition. What is the fibrate fillet Julia? What is the fibrate fillet Julia set? So, the field Julia set is defined like this, at the set of points in T times C, whose orbits do not escape to infinity. This definition is entirely analogous to the classical case. Now, for the Julia set, here we have a difference, subtle, but it's important. Since we're talking about fibers, we have to define first what a fiber in the from the field Julia set is. So this is now from this fiber over T, we take the topological boundary of the set. Now we take the union of overall these fibers of this topological boundary, and then we take this closure, and it's what we're going to call the Julia set. Well, of the fibrate polynomial. Later, we will see that this definition of the Julia is relevant. Now, well, when I start this talk, I mentioned the importance of hyperbolic systems. And I told you that this definition is entirely related with the definition of Julia set. So a polynomial is hyperbolic if satisfies these conditions. That is equivalent to say that is uniformly expansive on the Julia set. Thanks to Sester, the first significant result of hyperbolicity is that for hyperbolic polynomials, the fibers of the Julia set moves halves-of continuously. Well, remember that hyperbolicity is related to the behavior of the orbits of the critical points for the classical case. But here in the fibrate case, things are more complex. Here, the critical set has the same topology that the base space. So the first theorem, or the main theorem of Sester's thesis, is this one, and relates the hyperbolicity and the critical sets. There are four following equivalences, and well, the first one that P is hyperbolic, but the important one is this, the number 4, that says the postcritical set is disjoint from the Julia set. Again, this last point is analogous to the classical case. Also, Sester established a result like the Fatou lemma. And what it says is that there is always a relationship between the stable set and the critical set. However, in classical dynamics, the Julia sets coincide with the topological boundary of the field Julia set. This is not necessarily true in fibrate dynamics. But there is always a well-defined, a well-defined contention, this one. The Julia is contained in the boundary of the field Julia set. So here is a counterexample of what I just told you. consider this fiber quadratic dynamics, sorry, and here. In the picture, we can see that the dynamics in the fibers T sub 0 and T equal 2 is static here. So it stays on the fiber. And then the Julia sub 0 will be the unit circle, and the field Julia of this fiber will be the closure of the unit disk. So, and see how C of 2, like this, it's equal of -3. The Julia sub 2 will be a Cantor set, and the field Julia of the fiber has empty interior. On the other hand, in the remaining fibers, these ones, the dynamics move to the right. So to the fiber T equal 2. So also in these fibers, each Julia sub T will be a Cantor set with field Julia set of empty interior. So this is the difference. In this way, we have a difference between the boundary of the field Julia set and the Julia. So it is not difficult to see that this polynomial is hyperbolic. So Julia's fibers moves continuously, but not the fibers in the field Julia. So it is essential to make the following question. When does equality happen? And we find sufficient conditions for a hyperbolic case to get this equality. So to do this, we're going to restrict ourselves to an irrational rotation. Our definition of a fibered quadratic polynomial is going to be now this one. And the base space is the unit circle, and the function is an irrational rotation. Here, we highlight the dependence of the coefficients of the quadratic polynomial. Now, so we have the same fiber, but we move based on an irrational rotation. And we get the following results. For these polynomials, the hyperbolicity is sufficient to have Hausdorff continuity of the fibers of the field Julia set. And as expected for hyperbolic polynomials, we get the equality. The Julia set coincides with the topological boundary of the file. So when we study dynamical system in the classical case, we study the determining which are the fixed point, the periodic points, and what is the dynamics nature of that. Here, we don't, and for do that, we use the multiplier. In this case, we don't have fixed points or periodic points. It's because we are changing a fiber each time. So, and of course, not periodic points, because this is due to the irrational rotation. The simplest object that extends this notion is something called invariant curves. And it looks like this. Well, sounds redundant, but an invariant curve is a curve that is, sorry, a curve is invariant is a set of is a subset of a total space is invariant under the action of the polynomial that. So you have a point of the curve, you apply the function, and when you move to the fibers, we fall back into the curve again. In classical dynamics, we have a multiplier, also here too. And we can look at it at the average of the derivative of the points of the curves that, and of course, with this new multiplier, we can make a classification of the curves like, well, depending on the value of this number, like attracting, repulsor, and indifferent. In his doctoral thesis, Mario Ponce, my advisors, studied the local dynamics and this multiplier, and things happen as they have to happen. If the curve is attracting, on average, it attracts. And if repulsor, it repels. And not only attract, but linearizes. Yes. For this, Mario defines two important things. What is an invariant tube and, well, an invariant curve first. Oh, sorry. Well, an invariant tube is a topological cylinder that is invariant under the action of the fibers polynomial. On the other hand, a curve is stable if there is a completely tube that contains it. Looks like this. And so we have that if the polynomial is hyperbolic, then every attracting curve is stable. Now, another of Mario's important result is that he constructs a whole family of quadratic polynomials, but with two attracting invariant curves. This can happen in the classical case. So this construction makes a difference between the classical case and the fibered case. To do this, take this ellipse and define this polynomial. Since c equals 0 and c equals 1 are fixed points, the corresponding invariant curves becomes invariant curves. So from the shape of the ellipse, it can be proved that both curves are attracting. The critical set is defined by this curve. And the critical curve intersects all the invariant curves. So both basin of attractions will have contained critical pieces of the, no, sorry, will contain critical pieces of the critical set that. If the polynomial were hyperbolic, oh, sorry. This critical curve could not intersect the Julia set. So Mario was wondering, what about the parts of the critical set which are not contained in the basin of attractions? For this question, the following theorem arose. So we want to prove that Mario's family is not hyperbolic, but we know that the proof could be extended to the general case. So as stated in the theorem, if there are two attracting invariant curves, and there is a connected piece of the critical set that goes from one basin of attraction to the other, well, then we need to go through the Julia set. So by Sester theorem, the polynomial can be hyperbolic. So apply it to Marius family, we can see that that family can be hyperbolic. The set of hyperbolic fibered quadratic polynomials is not dense. So we use this to prove this, and well, the set of quadratic polynomials is not dense. Let's recap this construction. For each element of the Ponce family, we build a polynomial, a polynomial not hyperbolic, with two attracting curves. Then this condition is stable. So there is a whole open set around this polynomial that with the same property. So hence the no density. And thank you very much.
Thank you very much. Are there questions? Yeah, go up.
I was just wondering whether you have like a quick intuition why the MLC implies density of hyperbolicity.
Why MLC implies
Yeah,
what?
Density of hyperbolicity.
Density of hyperbolicity. Well, the only place where it's not proved the density is on the boundary of the Mandelbrot set. So one way to prove that you have a well-extended Riemann map is by knowing that the boundary is locally connected. So if you have the boundary is locally connected, then you have that each interior point is conformal to an open set. And that gives you the density.
Any other questions? If not, then let's thank Igsyl again. Yeah, I think we should start with the last talk of today. So this is by Sophie Schmidhuber, who will talk on the structure of foliations on dilation surfaces. Please go ahead.
All right, so hello everybody, welcome to this very last talk of today. I hope that you still have some energy and concentration left. So I think this talk should be accessible, so maybe there's not too much thinking involved, but so my name is Sophie Schmidhuber. I'm a PhD student with Corinna Ulcik-Rai at the University of Zurich. And as you can see, the title of my talk is called On the Structure of Foliations on Dilation Surfaces. And you can see the main character, as Sasha Skripchenko likes to put it. So the main character of today is already displayed here on the first slide. And this is a dilation surface. And maybe just a quick question for the audience, who in here has ever heard about dilation surfaces? All right, so there is a few. Who in here has heard about translation surfaces? A bit more, okay. So, so dilation surfaces are a natural generalization of translation surfaces. And they are defined as follows. So if you consider a collection of polygons in the plane, and we require the edges of these polygons to come in pairs of parallel edges. So for example, around here, you have those two red edges that are parallel to each other. You have the two blue edges that are parallel to each other. And the big difference to the case of translation surfaces is that we do not require the length of these edges to be the same. So if we have a collection of polygons like this, then what we can do is we can glue these two edges using maps that are compositions of translations and dilations. So using maps that are compositions of the form z goes to lambda z plus v. And if we do this, then what we get is a surface that has this dilation type structure on it. So in this example here, I think everybody knows that if you identify the two sides of the square, then you get a torus. And here we also have this pink segment that will end up becoming a boundary component of this torus. We get these two tori, we glue them together along the boundary component, and we end up getting this genus 2 surface with this dilation structure on it. And this surface is what we call the two-chamber surface. So it's also one of the first examples that have been studied of dilation surfaces. And what I have not talked about just now is what happens to the vertices after gluing these polygons. So if you look at the vertices, what you can do is you can imagine that you're a little ant that starts somewhere over here and starts crawling around this vertex counterclockwise. And what happens is, so you start over here, you start crawling up to this blue edge, then you go back down, then you come out at the red edge, right? Then you go from the red edge all the way down to the pink edge, and you enter the other polygon, and then you go from here down here. And so in this particular case, what happens is that actually all of the vertices project to the same point on the surface. And the angle that this little ant is passing is what we refer to as the cone angle around the singularity. So this cone angle, just by definition of a dilation translation surface, is going to be a multiple of 2 pi. And it will look something like this. So here in this picture, all the vertices project to the same point. We have a cone angle of 6 pi. And it will look something like this. So we take 6 copies of pi, we glue them along. So, I mean, we have this dilation structure on this picture here. But the singularities will look something like this. So definition of a dilation surface is really a surface that has this affine structure together with a finite set of singularities, where around the singularities we're homeomorphic to a K-sheet covering of the complex plane. And now we are dynamicists. So what we want to do is we want to do dynamics on these surfaces. So what we're going to do is we're going to define something called a directional foliation. So a directional foliation, I mean, it's as easy as it gets. So we take we pick an angle theta in S1. We could pick a point P on the surface, and we just start going in direction theta on the surface. And what happens is that we get this straight line in direction theta. We can do this because translations and dilations, they don't really affect our angle. So they don't change our angle. So these kind of foliations are still well defined in the affine world. And if we hit the singularity afterwards, this leaf is not well defined. But if we don't hit the singularity, we can do this infinitely often in the past, infinitely often in the future, and we get what we call a leaf passing through P on the two-chamber surface. And the union of all leaves in direction theta is what we call the directional foliation F theta on the surface. So what do I want to do today? So my main result that I proved about these dilation surfaces is that if you have a directional foliation, if you have a dilation surface, then there exists a decomposition of the surface into finitely many subsurfaces on which we can completely describe the dynamical behavior qualitatively. So there's really like a structure of the orbits on these subsurfaces that we can fully describe. And I don't think that I will have time to go into the proof of this, but I want to give you an idea of what are these 4 different types of behaviors that we can have, and then maybe give you some hint as to what exactly I use to prove this. So first of all, what is interesting, I mean, there is 2 types of trajectories on these surfaces. So some of them, or if you have a subsurface, then maybe a trajectory will enter the subsurface and then leave the subsurface again at some point. And those are somehow regions of transition. So if all of the leaves do this, then this is not particularly interesting for us. So what we want to look at is recurrent behavior. So we want to look at leaves that come back to themselves. So we call a leaf recurrent if it intersects any neighborhood of any point P in L. So if it keeps coming back to itself infinitely often. And that's what we call a recurrent leaf. And there is two cases. So there is leaves that we call trivially recurrent, which are just closed leaves. And then there is non-trivially recurrent leaves, which is all other recurrent leaves. And today I will give you two examples of trivially recurrent leaves, and I will give you two examples of non-trivially recurrent leaves. And yeah, and then show you that all the behavior somehow reduces to these four cases. So if we are trivially recurrent, there is the flat picture over here. So by flat picture, I mean this is something that can also arise in a translation surface. So imagine that you have two edges of the same length that are glued to each other. And now we take the vertical foliation on, or foliation, yes. And so we're not talking about flows, just to, I could, usually we talk about flows on translation surface, but we don't really have a well-defined notion of length on dilation surface because we dilate. So that's why I always talk about foliations, not about flows. But okay, so we have this vertical foliation, and all the leaves are actually going to be periodic, right? So you have the top part of the leaf and the bottom part of the leaf, they're going to be glued together. So this will project to a closed curve on the surface. So this is what we call a flat cylinder, and we call a foliation for which every leaf is closed. We call it completely periodic. And then we have this picture to the right, which is an affine cylinder. So if we imagine we have these two edges, and we say that the top edge is longer than the bottom edge, then what happens here is that the midpoints of these two edges are glued to each other. So if we now look at the vertical foliation in this case, we get the midpoint of this being glued to the midpoint of this. So if we take the vertical foliation, we will have a periodic purple leaf. And now any other leaf that enters this cylinder, the dotted lines here somehow indicate how we're gluing these two edges. So any other leaf that enters, it's going to start spiraling towards this periodic orbit. So we glue it, we go back down here, we come up, we glue it, and we start spiraling. We never go over this periodic leaf, but we just get closer and closer and closer. And this is what we call an affine cylinder of angle theta. And of course, we could have just reversed the lengths. Like we could have just said that the top one is less long than the bottom one, and then we get the opposite behavior. So we get a repelling closed leaf, where every leaf is somehow going away from this periodic leaf. And there is a name for foliations that have finitely many closed leaves that attract and repel any other leaf, and this name is called Morse-Smale. So if we go back to the example of the two-chamber surface, I colored in red and in yellow the two affine cylinders that arise on the surface. And now if we pick the foliation that connects the midpoint of these two red leaves and the midpoints of these two yellow leaves, then you can see that any other leaf, because here we always multiply with a factor 2, right? So we somehow get repelled from the top orange leaf, we traverse into the other chamber, and then we get closer and closer to the bottom orange leaf. So we go from up here, we go down here. So one of these leaves, this one here, is attracting, and the other leaf is repelling. And this is what we call Morse-Smale behavior. And there is a conjecture by Selim Ghazouani, who has done a lot of work on dilation surfaces, that this is somehow the typical behavior for the directional foliation on a dilation surface. So that for almost all dilation surfaces, for almost all directions, this is the picture that you should get. But yeah, there is a lot of the results that we know by now about translational surfaces, we can pose the analogous questions for dilation surfaces, but a lot of the results are not known yet. So this is one of the big open problems with dilation surfaces. So this was trivial recurrence. So we have a closed periodic orbit. And now what we can do is we can look at non-trivial recurrence. And I mean, okay, the easiest example of this is just the irrational flow in the torus. So you just pick an irrational angle and you start shooting in this direction. And what you get is a leaf that is dense, right? And this leaf is by definition recurrent. So this is what this is the easiest example of non-trivial recurrence, which we can also have in the translation surfaces case. And we call a foliation for which every infinite leaf is dense on the surface, we call it minimum. And now there is my favorite example of non-trivial recurrence, which is called the disco surface. So we actually had a very nice talk today already about Cantor attractors, or there was some example here of a Cantor attractor. So what I'm building here now is also going to be somehow yeah, it's going to be a Cantor attractor in one dimension. So why is this called the disco surface? I think it's kind of obvious, because if you color these the 4 affine cylinders that are embedded in this surface, then you get this disco light, right? And so this surface will be a genus 2 dilation surface with 2 singularities. And now what we can do is we can change the polygonal representation of the surface. So what we do is we do these 2 cut and paste operations. Cut and paste means so they are continuous, so they don't really change the surface you get after gluing. They change the polygon, they don't change the surface. So what we do is we cut here, and we paste this whole thing on the side to the left. And then we cut again from this singularity up here, and this upper triangle that we get, we paste it all the way here. And then what we get is a surface that, so the new polygonal representation will look something like this. And what I did here is I colored 2 subsurfaces. One of them is blue, and the other one is red. I called this one I called D1, and the other one I called D2. And now I pick a direction theta, and I start drawing 2 parallel lines in this direction. So if you consider this lower segment, that is the union of the green segment and the blue segment, and I take these parallel lines in direction theta, then when so what I'm going to do is I'm going to shade the complement of what is between these lines. I'm going to shade it in this subsurface in dark blue, and in this subsurface I will shade it in dark red. And then what I do is I follow the foliation, and I just sort of push these regions forward. So in the blue subsurface, what I do is I take this. So if you look at this blue region, this part up here is glued to this part down here, right? And then this part up here is glued to this part down here. So these 2 dark blue strips, after one iteration, if I move them forward, they join together in the middle to form a strip. And I do exactly the same thing, rotated by 180 degrees in the red subsurface. So what I do here is that I take these 2 red strips, I go in the past, so I go in direction minus theta, and I get this red strip that moves around here. And of course, I can repeat this procedure infinitely many times. And what I get is I really get this picture of a strip winding around this whole blue subsurface. And it becomes smaller and smaller and smaller. So every time I iterate, the length of the strip is divided by 1/2, right? Because I always glue with these maps of factor 1/2. And now the proposition is that if we take this dark blue strip to be open, and we assume it never passes through a singularity. So by this, I mean that it never actually hits one of these singularities. Then, and I look at the complement of all the iterates of this strip in the blue subsurface, then this complement is a Cantor set. And Cantor set in the sense that it is closed, it is totally disconnected, and it has no isolated points. So it is closed as the union of as the countable union of open sets. It is totally disconnected because you start with a strip of length 1/2 and you just divide it by the length 1/2. So in the end, you get something of length 1 if you take the union over all these strips. And no isolated points, because you can show that if the complement had an isolated point, then you would hit the singularity in the future. So what is happening here is you have 2 Cantor sets. One of the Cantor sets is in the blue subsurface, the other Cantor set is in the red subsurface. These Cantor sets are actually the closure of a non-trivially recurrent orbit. So non-trivially recurrent because there's no isolated points. So this if you take a non-trivially recurrent orbit that is not like this dense set, then it can really be the closure. The closure of this can be this Cantor set that has no isolated points that still somehow accumulates to every single point on the orbit. And we call a foliation Cantor-like if there exists a non-trivially recurrent leaf whose closure intersected with the cross-section is a Cantor set. So this is somehow the definition of Cantor-like. And if I just quickly go back to this picture, we have one Cantor set here, one Cantor set here. This Cantor set is an attracting Cantor set, meaning that every leaf that enters this blue subsurface, which is going to be, if it's not in this closure, it's going to be in this strip, right? And then this leaf in the strip is going to accumulate on this Cantor set because the strip just is exactly, the complement of the strip is exactly the Cantor set. And in the past, so somehow the dynamical behavior of this is that in the future you accumulate in one Cantor set, And in the past, you accumulate on the other Cantor set in the red subsurface. So we have an attracting Cantor set, we have a repelling Cantor set, and all the leaves are either attracted to one or repelled by the other. And okay, so this is what we call Cantor-like. And now my main result is that, so if you're given a direction of foliation on any dilation surface, then I claim that there exists a decomposition of this dilation surface into subsurfaces on which we can completely describe dynamical behavior in the sense that either these subsurfaces have no recurrent leaf, or they are in one of the cases that I just showed you. So either we have a flat cylinder where the foliation is completely periodic, or we have an affine cylinder where the foliation is more small, or we have minimal subsurfaces where the foliation is minimal, or subsurfaces where the foliation is Cantor-like. And then I put down here, I put the second part of my statement, which I don't think I really have time to talk about what this means exactly. But this is for the people that know about IETs and AIETs. So there is something called interval exchange transformations, which we've heard today already with Sasha. And affine interval exchange transformations are essentially, if I just quickly go back to this picture, is an exchange of intervals where you're allowed to dilate the intervals. So this red interval, these 4 intervals are shuffled around and they don't have the same length. So then maybe after the map, after we apply the map, we dilate or we shrink. So the first return map on a cross-section of a dilation on a transversal segment of a dilation surface is an affine interval exchange transformation. And what I'm saying here is that in this case 3 and case 4, the first return map on any transversal segment that intersects the non-trivially recurrent leaf is semi-conjugated to a minimal IET. So this is somehow saying that these, for example, this interval here is what you call a wandering interval. On the AIT, on the affine interval exchange transformation, this would be a wandering interval. And this wandering interval, you can blow it down to a point. So if you take this whole interval here down to a point, then you get a minimal interval exchange transformation. So you get a semi-conjugacy that really maps this to a minimal interval exchange transformation. And there are some very famous results by Mami Musayakos, which also gives you some type of so they state that for almost every IET there exists a semi-conjugated AIT that with a wandering interval that you can obtain with a construction like this, only that in this example here we have attracting and repelling Cantor sets. So we really have one wandering interval that goes in the future, one wandering interval that goes in the past, and they don't go either in the future or in the past. But that's a bit of a digression. So yeah, this is if you've never heard about this, then that's fine. How much time do I have? Because I forgot to time. 10 minutes left. Okay, so I'm a bit quicker than I was. 10 minutes with questions or without questions? Okay, good. So, okay, let me say a quick thing about the proof. So the statement follows from something called the Levitt decomposition or Levitt-Gardiner decomposition, which states that if you're given a continuous flow on a compact surface S with finitely many singularities, then there exist finitely many closed curves that cut this surface into components with at most one non-trivially recurrent orbit closure. So somehow the picture here is that you have a non-trivially recurrent orbit closure here and maybe one over here, and in between all the leaves just pass through. So they exist, I just didn't draw them, they just somehow pass through this whole, through the surface, and then you can cut your surface using these finitely many curves. And this already gives you a large chunk of this decomposition theorem for dilation surfaces. And I think this is really nice because it's a paper that was published in the 80s. So there was actually some very, very nice work done by Levitt and Maya and Gardiner and people around that time that were classifying these orbit closures and trying to understand these non-trivially recurrent orbit closures. And I like the fact that, somehow I was able to use this theorem from the 80s to talk about dilation surfaces. And then something else, so for this blowing down statement, so the construction of how to blow down these points, it follows from a paper by Carlos Gutierrez, which was also published around this time where he sort of describes how to blow down wandering intervals to a point to really get this semi-conjugacy. All right, so this is the past work somehow, and this is just one slide on what I'm working on right now together with Corinna Ulcikrai, which is about trying to find an algorithmic way to get this decomposition. So if you're given a fine interval exchange transformation or a dilation surface, for those who don't know what this is, then you can then we want to use Rosy-Veach induction to algorithmically detect these non-trivially recurrent regions. So we use something called a combinatorial rotation number to figure out where exactly these non-trivially recurrent regions are. And then we sort of want to develop an algorithm where we put in any AIT and it will sort of spit out exactly where these, what these different regions, like which regions belong to which part of the decomposition. All right, so that's everything I wanted to talk to you today. Do you have any questions?
Yeah, so thank you very much. Now we have plenty of time for questions.
Yeah, maybe
there's already a question.
So for translation surfaces, we have some understanding of like what they look like over, because we can break them into strata.
Yes.
Is there anything like that for dilation surfaces?
So there is people that are working on the moduli spaces of these things. But we have not really, so for example, I think there's no way there hasn't been like a measure that you could find on these strata or something like
And there's
that.
no flow on them?
Yeah, and you don't really have a flow because it's you don't have a distance on these surfaces, right? So there is I think Jain Wang is a student of McMullen, used to be a student of McMullen. She has been writing some very interesting papers on the moduli spaces of exactly these dilation surfaces. And this is exactly one of the directions that people are exploring right now, of trying to find more information.
Are the strata like orbifolds? Do we know anything about what they look like?
I'm not completely sure. I'm actually not 100% sure how far the theory has been developed for them in terms of moduli spaces. But maybe some people in the audience know.
Other questions?
Can you go back to your film?
Yes.
Yeah. So is there a way of, okay, I know a little bit more about AIETs. So is there a way of describing this in terms of AIETs?
Yes, exactly. I mean, this exactly the same statement is true for AIETs. Just that, so you have, I mean, the statement just goes that you can break up the domain into finitely many unions of subintervals on which then, I mean, yeah, you just partition your interval on which the AIT is defined into finitely many unions of subintervals, and on these unions of subintervals, you have one of these 4 different types of behavior. And yeah, and this is just going to be that it's not just the first return map, but really the AIT defined on this.
Okay.
Union of size. I mean, this is talking about dilation surfaces or AITs. It's somehow the same thing. So yeah, that's exactly that.
So the foliation is the orbit in that context.
Exactly.
Okay.
So it's, yeah, it's really this picture. I mean, I'm not sure how many of you have really seen these pictures, but I mean, if I take the vertical foliation on this guy, right, then and I look at the first return map, then it's going to give me exactly the AIT that is somehow.
Okay. Yeah. Thanks.
Other questions?
Your last slide reminded me of some work of Boschonitsa and Carol. When the parameters were quadratic, there was some kind of self-similarity. Would it make sense in this context to have something similar? When you have quadratic parameters and in the Rosy-Veach induction, do you...
So I'm not, so I know what self-similarity means. I'm not sure what you mean by exactly.
That the Rosy-Veach induction was periodic, in fact.
Yes, exactly. So we were thinking, So yes, we're not assuming this, but we were actually thinking of trying to assume something like a self-similarity, because so somehow what we're working on quite a lot right now is trying to find out when exactly are these non-trivially recurrent orbit closures, like the Cantor sets. They can be attractors, they can be repellers, they can somehow do both, as in this Mariam example, where you have attractors and repellers. And we have the feeling that if you put some extra conditions on, like for example, self-similarity, or also something like that, you have some sort of invariance of this IIT or AIT, that it's actually easier to deduce statements about when something is an attractor, when something is a repulsor. So we're sort of looking into trying to impose these kind of conditions and what we can say about this attracting repelling behavior. Yeah, I'm not sure if this answers your question.
Sure. Yeah. Yes. Thank you.
Other questions? No? Okay, so if not, then let's thank Sophie and all the other speakers of the afternoon.